Bryn, welcome back, buddy.
Glad to be here with you, sir, and
Part
with everyone
4.
else.
We made it. We're in the last blast of this class. And believe it or not, this is the fun part. This is where we get to show everything we've been talking about through live, I call it live, through captured case studies. Now, this isn't some made-up stuff we fudged to make look pretty for the class. These are actual cars I worked on. Actually, some of them Bryn worked on. I might not be able to share everything that Bryn did. But we've got 10 to 15 case studies possible that we may or may not get through all of them, but it doesn't matter. We're going to demonstrate the technique and how to use the tools and capture the data so we can analyze this. So I'm going to share my screen, and the first thing I want to remind you guys of, give me one moment here. Can you see my screen, Bryn?
Yeah.
Okay, good. I don't know why. It didn't look right to me. I want to talk about generalized testing versus pinpointed testing. And this is very important because I find, especially when I was younger and less experienced, I'd go to class and I'd learn a new technique. And I'd come back the next morning with some pep in my step, wanting to practice these new techniques. And I found myself implementing them on a car I had no business doing that for. If that makes sense. You know, there was no reason to do that test. I just wanted to incorporate it for some reason, and I wasted a lot of time. So what I want to remind you of is that pressure waveform acquisition and analysis on rare occasion can be a really quick go-to test, something very, very easy to perform to yield you some information, to give you a generalized direction. But on more often than not, we are going to be following the test results from other more easy to perform tests, ones that yield us a lot of information with a very little bit amount of time or energy invested. And I want a reason to perform pressure testing. So if that makes sense, please raise your hand. I don't want anybody going back to the shop and getting out the pressure transducers because you just want to put them on a car. I mean, I welcome that, but keep in mind there's a time and place, and practicing on cars and wasting time during shop hours might not be the best practice, especially long-term regarding job security. So keep that in mind. But regarding generalized testing versus pinpointed testing, again, the idea is to perform these relatively simple tests. That's why I call them generalized. They're going to give us some information without investing a lot of time or energy. That's why I call them generalized tests. And every time I get an answer from a generalized test, it's going to lead me in a direction. I want to follow that direction, like follow the cookie crumbs. And if I get myself focused on my game plan, I don't waste hardly any time, even though it appears I'm taking my time, and to the untrained eye or the impatient, it might appear I'm wasting time. But in the end, I likely get to a conclusion a lot less sweaty than other technicians. So let's grab the low-hanging fruit first, the easy-to-grab information to make diagnostic decisions. So if you look at my PowerPoint screen here, we've got the generalized tests here up here in red, and they are going to lead down to one of three particular areas. Now, I call these areas funnels, and I call them that for good reason. My mentor, Jim Morton, referred to these funnels as such. And I asked why, and he explained it to me very simply. He said, listen, think about a drivability fault you have. Let's call it a misfire or low power or a chug or something like that. If it's not transmission related, of course. An engine's going to perform improperly for basically one of three reasons. Either we've got a problem with engine mechanical integrity, like jumped timing or a restricted exhaust or a collapsed inlet, right? You know, a big bird's or a rat's nest inside an airbox. So we've got an engine mechanical integrity problem, a breathing issue because an engine's an air pump. Or we have an improperly fueled engine or cylinder, right? We don't have the right air-fuel ratio. Or our ignition is insufficient, meaning we have a coil that cannot produce a strong enough spark, if any at all. Or maybe the spark is perfectly fine, it's just being discharged at the wrong time. We know that'll cause a drivability fault. So my initial approach as a diagnostician is to not fix the car. I don't care what's wrong with the car. I want to find out what area the fault lies in. And if I can get myself into one of these funnels, we call it a funnel because start big and generalized, and every test I do is going to drive me further and further and further down the funnel till I'm absolutely pinpointed. And a lot of times that means committing to removing an intake manifold and removing a spark plug and going in cylinder. Now, somebody mentioned here in chat, it's going by the name Galaxy, looks like J3. He said a knock sensor can feel that way. Absolutely. What is the knock sensor going to alter? It's going to alter spark timing. So that would fall into the ignition funnel. I hope that makes sense for you. Those are the basic, probably the common denominators, those three areas right there. So whatever funnel I'm in, I'm going to stay in that funnel. If I crank an engine over and I hear one hole that sounds dead compared to the other 5 or 7 holes, I'm not going to chase an oxygen sensor problem, right? A sensor input problem. I'm going to be staying in that mechanical integrity fault funnel. And I'm going to do another test that gives me even more information, even if it takes a little bit more time. And if that answer drives me further down the funnel, I'm going to get even more pinpointed. So that's the idea. This is what helps keep us efficient and accurate without skipping any necessary steps. So the idea behind these 3 funnels is to perform whatever test is going to put me in a funnel the easiest. And I find whether I think I have an engine mechanical fault or I think I do not have an engine mechanical fault, I myself am always going to perform a relative compression test first. Sometimes that's just me listening when I hit the key. Sometimes I might venture under the hood with my amp probe and my lap scope. Sometimes I can't find an easy area to place my amp probe, so I will use voltage drop, which is basically the same test. It's just inverted. So an engine mechanical integrity test by way of a relative compression test is going to be one of the tests I'm going to perform first. Now, the idea behind a relative compression test, if you guys are not familiar, is a piston, once it harnesses air, and of the 4 strokes in the 4-stroke engine cycle, the compression stroke is going to take the most toll on the starter. It's going to be the hardest to perform. Now, starter load equates to compression. They relate to one another. As compression goes up, that force that's applied to the top of the piston increases, so does the load on the starter. With that being said, as load goes up, so does current flow through the starter supply circuit. So if we can measure the current flow, we can basically infer starter load. Well, we're going to do that with this device here called an amp probe. Now, I know a lot of you at home are very familiar with this device, as I am, and so is Bryn. But the significance of this device, if you're not familiar, is that this amp probe is going to basically measure the magnetic field around the wire. Now, I told you that to tell you this. Just like current flow relates to starter load, the magnetic field relates to current flow. So the more current that flows through this wire, the stronger that magnetic field is around the wire. What this device does for us is it measures the strength of that magnetic field, and it outputs a voltage that correlates to that current level. So for instance, if you look closely here, this is a very poor resolute capture to see these numbers here, but this will give us a range, a conversion chart. And what it might state is for every 100 milliamps that flows through these jaws, 1 millivolt of voltage comes out. There's other amp probes, larger ones that we like to put around a battery cable, and the math can be even easier. For every 1 millivolt of current flow that goes through the jaws, 1 milliamp, 1 millivolt comes out. So if we see 10 millivolts on our lab scope, how many amps does that equate to? Somebody mind typing that in chat? I'd really appreciate that. 1 millivolt would equal 1 amp. 100 millivolts would equal 100 amps. So let's get on with the test. If I were to place my amp probe around a battery cable and I'd hit the key and crank the engine over, there's lots of information here that we're simply not going to use. But I just want to tell you the power of using an amp probe. I can see right here, this initial bump that we see right here in this area is the current flowing through the solenoid windings. And we have what here we call a pintle bump. And that infers mechanical movement. When you move a ferrous metal within a magnetic field, it diverts the current flow a little bit, creates a deviation. So that bump signifies to me that the solenoid did in fact engage. As soon as it does engage, we know we now have current flowing through the starter windings. And we have this huge, huge spike here. And I know you don't see any numbers reflecting the amplitude of this spike, but I can tell you this is probably on any conventional 4 or 6 cylinder engine. Brent, I've seen 700-800 amps or more sometimes. What about you? You're muted. You're muted. Your mic's muted.
Sorry, bud. Yeah, what I've found for years, I used the 600 amp clamp, right? That was the most common inexpensive clamp, and it was almost always, cut off. It was always peaked out.
Like maxed out, like it went off the screen, right? Yeah. I got to tell you guys, in the fairly recent past, I don't work on a lot of diesel engines, but I was working on a Chevrolet truck with a Duramax diesel engine in it, and the inrush current, when I first hit the key, exceeded 1,300 amps. Now, I want you guys to think about something for a moment. Picture we've got a car outside in the parking lot that we have to get inside, and it has 4 flat tires. Now, we usually put the skinniest guy up in the driver's seat for good reason, right? He's going to make the car less heavy, and we usually put the big bruisers behind the rear bumper. Now, think about when we try to get that car to move. Everybody drops down real low, digs in deep, probably grunts a little bit to get that car moving. But once we get the car rolling, isn't it far easier to push that car down the street? Across the parking lot? The same happens with current flow. When we initially hit the key and the starter energizes, the current flowing through the starter windings is initially very high, especially when the starter comes in contact with the ring gear and it starts to attempt to drive the engine over. As the engine begins to move, the load on that starter starts to subside, and as a result, the current flow begins to decrease a little. So again, there's lots of information here that's very valuable to us if we were evaluating the mechanical health of the starter circuit or the electrical, the health of the circuit itself. But we're not concerned with that in this case. We're concerned with this area right in here. When the starter amperage starts to level out and we get these peaks and these valleys, this means something to us. Now think about this here. If I hit the key and the engine starts cranking over, we know of the 4 strokes, intake, compression, expansion, and exhaust stroke, we know that compression stroke puts the highest load on the starter. So every time a piston comes up to top dead center of the compression stroke, the starter load is significantly higher. And that's what this signifies right here, this peak. The next peak signifies when the following cylinder in the engine configuration firing order achieves top dead center. And the next one, and the next one. So please raise your hands if you agree with me that all of these cylinders, relatively speaking, are similar to the other 3. And that's exactly what I see here. Do you see that too, Brent? Do you see that all the cylinders are relatively the same?
Yep.
So, hey, humor me, pal. What does this engine sound like? You've been here a million times. What does this sound like? They all sound the same. Wouldn't you guys agree? Every cylinder loads the starter the same. But, Brent, I'm going to call on you one more time, my friend. What does this one sound like? Yep, there you go.
I even
well, you
moved
guys,
with it.
we've all heard it, right? We've all heard it with our ears when we hit the key. But now you can see it. What you hear with your ears is a change in crankshaft speed because the load from one of the pistons goes away. I shouldn't say goes away. There's always a little bit of load, but it's far less than a cylinder that has integrity. So we've got one starter, we're going to call it a hump, okay? We're going to call it a starter hump, a good one that reflects the same value or very similar, a third one, and then look here, one's missing. So like Brent said, we've got da-da-da-da, 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 right? We've got that repetitive sound. Somebody place up in chat, please. How many cylinders is in this engine configuration? 4. Can anybody tell me which of the 4 cylinders is creating this hump? Good job, Ben. No, you can't. The reason being is we don't have an ignition sink. We don't have a point of reference to say, this is when cylinder number 1 is on top dead center, or this is when cylinder number 4 is on top dead center. So doesn't it make sense that if I pull the car in my bay, maybe I heard this out in the parking lot, right? I heard da-da-da-da-da-da-da-da-da, and I know I've got an engine mechanical fault. I'm going to put my amp probe on there, and then I'm going to add a second channel. And adding that second channel doesn't really mean anything until you know what. I might add an ignition sink. Maybe I know it's on cylinder number 1. Exactly. I need to know the firing order. Please don't make the same mistake others have made in the past. Unless you are 100% sure of the firing order, please do not guess. It's not worth that time that you skip over the invested time to research it. What that means is if you're wrong, you are taking the wrong cylinder head off the car. So, and I've seen it. Believe me, I've seen it. So don't guess. But at this point, I know I have to grab an ignition sink because right now this just tells me the only information on the screen regarding engine health is that one of the 4 cylinders is not contributing like the other 3. Now it's time to find out which. So if I told you the firing order is 1, 3, 4, 2, and I then told you I put an ignition sink on cylinder number 1's ignition coil. Maybe this is a 2-wire COP system, right? I've got a power feed and then a ground control. I'm on the ground control of 1 coil and it's cylinder number 1. Follow me, if you will. Follow my cursor here, my mouse cursor. This is cylinder number 1's ignition strike. That makes sense that it happens very close to top dead center for cylinder number 1. So this peak represents cylinder number 1 top dead center event. If you agree with that, if you're with me, please raise your hand. Wonderful. So that's cylinder number 1. This would be cylinder number 3, right? Here's the firing order, 1, 3, 4, 2. So 1, 3, 4, 2. 1, 3, 4, 2. 1, 3, 4, 2. 1, 3, 4, 2. Do you see how easy that is? Bryn, how long did this test on this car take? And you've done it a million times, honestly. You leave your scope on, right? You turn it on with the coffee pot. You pull the car in your bay, you open the hood. I know all you do is turn around and grab your scope and put it on the car.
I don't even look. I don't even look anymore.
Right. How long does this take to do, honestly?
Between 5 and 10 minutes. Start to finish.
And that's if you're really fumbling around, right?
Yeah.
And it's okay to take that long, but the more often you do this, just like tying your shoes, it's just something you can do automatically. So right now we know cylinder number 4 is my suspect cylinder. Let's pretend this is a V10 engine. Let's pretend I'm working on a Ford Carpenter van. And I use this example all the time because it really hits home. With a V10 Triton engine, right? And it's got that big ugly dog box inside, right? I'm not taking all 10 spark plugs out to do a compression test. If I'm even going to do a compression test, I'm only going to pull 1 out. And you know me, it's not the one, it's not cylinder 10 and it's not cylinder 1. It's always like cylinder 4, right in the middle of the engine where somebody's got to hold the cuffs of my pants so I don't fall in, you know? So it's that generalized testing that's going to lead us to the pressure waveform analysis, because the pressure waveform analysis is a bit more involved. But think about it this way. If I already know I have a mechanical problem, doesn't it make sense that even if I invest more time grabbing my pressure transducers and researching a firing order, that I'm definitely going to see more information? I know I'm on the right track. Please raise your hands if you agree with that line of thought. Good, then you're right with me. However, if I did not do the relative compression test and I was kind of shooting from the hip, you guys see it all the time. Somebody does a compression test and then they do a fuel pressure test and then they go for another road test and they come back and then they want to move coils around and then they want to drop an exhaust system. And they're hoping to run into the problem. They really don't have a game plan. I used to do that when I was younger, before I established a game plan, and it wasn't fun. So relative compression testing in most cases, almost all of them, leads me to mechanical analysis by way of the pressure transducers and the lab scope. And the reason being is it gives me, it's justified reason to invest more time, and still it's even better than disassembly. So I'll capture and I'll analyze data from the intake, the tailpipe, the crankcase, the cooling system. Sometimes I do all four at the same time, right, Brand? I got an 8-trace lab scope at my disposal. I could capture all this and ignition and crankshaft position sensor. I could put these probes anywhere I want. But, you know, you can do these one at a time or multiples at a time and turn channels on and off as you see fit. As you become more comfortable with this, you can add more channels. So what I'd like to do now is, is transition into the fun stuff. We are going to work on cars that were actually in my bay or in some of my really close friends' bays, guys that I trust and have given me the information and showed me the test results. You know, conclusively, we decided what was wrong with the car, and I can present these case studies with confidence. So I want to start off first here with this 2003 Buick Century. We're going to start nice and easy, and keep in mind, the way I'm presenting these case studies is not to get to the root cause of the problem as fast as possible. I'm purposely going to take the long way around, implementing different tests, sometimes unnecessarily, as part of a learning phase. The best way to learn is when you already know what's wrong with the car. Would you guys agree with that? If you already know what's wrong with the car, I'm no longer implementing tests to see if there's a problem with the car. I'm now implementing tests, even new tests, to see if it lines up with what I already know. So that's what I'm going to be doing in most of these cases here. So this first one here is a 2003 Buick Century. Now, again, just like we did in phase one of this class, is I'm going to tell you what is wrong with the car. And you guys have probably seen this a million times. Those of you guys that frequently work on these 3100 and 3400 series engines from GM. One of the intake rockers has fallen off because the threads ripped out of the pedestal. And we'll get to that, though. I want you guys to know the answer to the case study, the answer to the riddle, so you can focus on the tests I'm performing and the results of those tests. So here's the problem. The car came in misfiring and running very poorly. There was a DTC P0300 stored. And when I got in a car, again, the best tool you own is the one between your ears. And I always use as many senses as I have to help aid in my analysis. So when I hit the key, the first thing I heard was that dead hole, like that demonstration Brid did, that da-da-da-da-da. That's a variation in crankshaft speed because there's a variation in load from cylinder to cylinder. So I'm going to perform a compression test, a relative compression test anyway, even though I already hear that there's a mechanical fault. Somebody please tell me why in chat. Why am I doing the RC test? Why am I doing the RC test, the relative compression test? Even though I hear I have a mechanical fault. Exactly. I want to identify which of the 6 cylinders has the problem, right? We've got the front bank and we got the back bank, and the back bank is up against the firewall in this car. And my forearms don't fit too well back there anymore. So I don't want to go back there unless I absolutely have to. The relative compression test is going to confirm, you know, whether I got to go back there or not. So we're going to start off with the relative compression test. So I could hook up my amp probe, or I can go across the battery and look at voltage drop. But in this example, my amp probe was quite easy to put across the starter circuit. Now what we have down here in red, which although it's really small because I'm not zoomed in tight, I've got an ignition event for cylinder number 6 and another ignition event for cylinder number 6. And those of you that look closely will recognize there's an event here that occurs halfway through the cycle. And if you're familiar with GM and this platform, this utilizes a waste spark system. So I can already anticipate some of the questions that might occur with this type of system is, how do you know if you're on compression or exhaust? And if you know anything about ignition analysis, compression loads the ignition system. It's very hard to fire a spark under pressure. It's very easy to fire a spark under atmospheric pressure, relatively speaking. So ignition system is going to be loaded. We're going to have a higher kV demand when a cylinder is under compression than we do when it's on its exhaust event or waste event. And that's exactly how compression sense ignition works on some of these systems. So we see the high firing kV and a low firing kV. We know the high firing kV to be that of our compression stroke. And when it repeats itself, that's 720 degrees later. Now, I've implemented the piston chart that we talked about yesterday. And excuse me, yeah, that was yesterday, wasn't it? No, that was the day before, Monday. Sorry, I'm losing my mind here. And we've applied it here to aid in analysis. And what this chart shows me is, if I know this is cylinder number 6 because I've referenced the ignition strike, that would mean this starter amperage peak is from number 6. The firing order is 1, 2, 3, 4, 5, 6. So if I start with 6, I've got 1. This would be 2, but it's missing. 3, 4, 5, 6. Please raise your hand if you see what I see. That cylinder number 2 does not load the starter the same way. Now let's just take a moment and look at the chart. Cylinder number 2's induction stroke starts here. 180 degrees later, it ends at bottom dead center. And now we start our compression stroke. Here's bottom dead center of the compression stroke. This is top dead center of the compression stroke, where pressure is the highest. So we know that cylinder number 2 is lacking compression. So I know the firing order. We have an ignition sync. We can easily determine that cylinder number 2 does not make the starter work as hard as the other 5 cylinders. Excuse me. So we're going to pursue a problem with cylinder number 2. Now, please raise your hands if you agree with me on this. This statement I'm about to make. Don't I have enough evidence? You guys can't raise your hands.
They're already raising their hands. You haven't even
asked. Put your hands down. I got to ask the question. You guys are cheating. Okay. Seriously, hear me out. Put your hands down. Put your hands down.
They would agree with you no matter what, Brent. You're so beloved.
Oh, please. Okay. Now, think about it like this. The relative compression test states cylinder number 2 is my dead hole. For whatever reason it is, that cylinder cannot load the starter. Don't I have enough evidence right now to pull number 2 spark plug out and go in cylinder? I do, don't I? I'm purposely, if I was doing this now, I might go directly in cylinder, right? But we're learning now. Let's pretend this is you back at the shop and you have some free time. You know, maybe it's a lazy Saturday afternoon. Hopefully not, but maybe it is. And now you want to take the long way around to implement some more tests that may put some more arrows in the target. So although it makes sense that I can go in cylinder now, I'm purposely going to take the long way around and go maybe in the intake manifold or in the tailpipe, or maybe both. Or maybe I'm going to do the intake and the tailpipe and in cylinder at the same time. It really doesn't matter. But right now I want to go in the intake. Why? Because I'm already under the hood. So we're going to do that same cranking test, but rather than looking at the amp probe or the amp probe by itself, I'm going to put my vacuum transducer or my delta sensor, right, or my WPS on the intake manifold. In this case, I'm using the ATS scope, and they make the vacuum transducer. So what we see here is an ignition command in red, another ignition command in red here, and here's the shorter, the waste spark event. So we know this is cylinder 6. And we know this is cylinder 6. And this squiggly line you see right here is the intake waveform. Now look at this. Wouldn't you agree that this doesn't tell me much the way it is right now? This is the raw file. I don't have anything implemented. I've got no special tools. I'm not using the cursors right now. I don't have a piston chart to help aid in analysis. So it looks like just that, a bunch of squiggly lines. We are not yet ready to analyze this. We have to prepare the waveform for analysis. So what I have here, those of you that are familiar with this, a lot of our friends maybe in Europe or over in Australia may not be familiar with this engine, but what we have over here is the inlet duct leading to the throttle body. And right behind the throttle plate is a T. It goes right down into the back of the throttle body that sources engine vacuum, and vacuum goes this way to the back valve cover, the PCV breather, and it goes this way, to the map sensor, and it goes this way to the PCV valve. So what we're going to do is we're going to take that little elbow off the PCV valve, and I'm going to put my pressure transducer, my vacuum transducer, directly in it, because this goes right to a centralized location on this engine. So again, the blue trace is vacuum, the red trace is ignition. And remember, I'm using a vacuum transducer. So when vacuum goes up, gets stronger, which way does the voltage output go from the sensor? It goes up. It's not a pressure transducer. When vacuum goes up, the trace goes up. When pressure increases, the trace goes down. So this, again, is not ready for analysis. We're going to have to partition this, right? So this is a 6-cylinder engine, and I'm sampling from an area that is common to all 6 cylinders. How many ways am I going to partition this waveform for analysis? How many ways am I going to partition this 6-cylinder waveform? 6 ways. Does that make sense? Not 4. 4 ways would be if we were going in cylinder, but this is a common area for all 6 cylinders. So we're spanning the cursors. Again, vacuum makes the trace go north. And I've partitioned it. I've put my white cursor here and another white cursor there. And then I came up here and I configured this for 6 cylinders. And I pressed this button right here, mark cylinders. And what that did was partition this waveform 1, 2, 3, 4, 5, 6 different ways. So we're prepared to analyze this now. We're ready to rock and roll. Now we have to see how each one of these 6 cylinders contributes to the intake manifold. And what do we have to keep in mind? Number 2 is our suspect cylinder. The question I'm going to be asking myself is, Bryn, how the heck is number 2 affecting this waveform? Does that make sense? So that's what I'm going to be doing. So what we're going to do here to aid in analysis, because I have access to this chart, we don't need this, but it certainly helps, and you'll see here in a minute. I've researched the firing order on this engine. It's 1, 2, 3, 4, 5, 6. And again, our ignition strike right here is for cylinder number 6. So when I build this chart, I'm going to pick the firing order, and I'm going to tell the chart, start the firing order with cylinder number 6. 6, and then it goes 1, 2, 3, 4, 5. Please raise your hand if it makes sense how this chart is displayed. Excellent. Okay, so we're going to stretch this chart like this and like this, and we're going to reference it right at our ignition strikes, because those ignition strikes represent top dead center and top dead center. So here's what we see. Vacuum makes the trace go north. Here is an intake pull. Which intake pull is it? Cylinder number 3, right there. The next one, cylinder number 4, and then cylinder number 5, and then number 6, and then number 1, and then, cylinder number 2, our suspect cylinder. Remember our relative compression test? Cylinder number 2 is not contributing to the intake. I don't know what's wrong yet, but I see this, and this bothers me. But I'm getting excited now because I know I got a problem with cylinder number 2, and I see cylinder number 2 is not contributing to the intake. But I also see something weird going on here. I see intake vacuum building and building and building, and then it drops off. And then I got a vacuum pull and another vacuum pull. So I really don't know. The first time I saw this, I had no idea what was going on here. But we're going to figure it out together. But this is where we should be focused right now. Cylinder number 2, right here. It starts its intake stroke right here, and we've got no contribution to the intake manifold when cylinder number 2 is supposed to contribute. So we're going to pursue this. So to answer the question, again, I don't know what's going on here, but I do see that cylinder number 2 is not contributing to the intake. So now I'm going to go in cylinder, and we're going to see what's going on here. So I want you to ignore the red trace. That was for my own personal gain, and I chose not to display it in this case study because we're not there yet. But the yellow trace is this blue trace. Now hear me out. You guys have all been here 1,000 times. Hey, Steckler, pull this car in and get a look at it. And you just, you got the hood open and you're running around, and just when you're getting into what you want to find out, they say, pull that car out, right? I have a weight or oil change. You guys know what I'm talking about. So I pulled the car outside, maybe half hour for an hour. And then I pulled it back in to take over where I left off from. So what you see here zoomed in is this blue trace. This yellow trace is the same exact trace. I just put a different test lead on it, okay? And if you look closely, you can see an intake pole here, and one here, and one here, and one here, and one here, and the fifth one, and then there's a missing intake pole here. And then the process starts over again. So first of all, let's look at this in-cylinder trace. How much compression do we see here? Please type that in chat. How much compression do we see here? How much compression? About 12 PSI, right? Now look, we got relatively straight towers. Even without cursors, we see we got fairly even pockets. Please raise your hand if you agree. We got pretty even pockets here. So 12 PSI, that makes sense that it doesn't load the starter the same as the other 5 cylinders, which would also mean why our relative compression test revealed that cylinder number 2 was lacking compression. But do we have a leak in the cylinder? Yes or no? Do we have a leak in this cylinder? No, we don't have a leak. And how do you know that? How do you know that? The pockets, right? Straight towers and even pockets. We know if we had a leak, right? It went like this. We'd be pulling a vacuum when that piston comes down. And that exhaust pocket would pull way down low. Let's do this. This exhaust pocket wouldn't do that. It would come down here, right? It would come way down. But that's not the case here. So the straight towers and even pockets tells me I don't have a leaky cylinder. Now, what else do you see? What do you see over here? Let me get rid of my pen. What do we see right here? We see rounding. What does rounding mean? Did that intake valve open? That intake valve did not open. So if I didn't open up my intake valve, can I fill the cylinder? Yes or no? And if I can't fill the cylinder, right? If I can't fill the cylinder with air, am I going to build any compression really? I'm not. Therefore, my relative compression test will show weak for cylinder number 2, and it will also show no cylinder leakage by way of the pressure transducer. Now, the intake trace tells you why. If vacuum goes this way and a lack of vacuum or pressure drops down, do you see cranking? We produce about 3 inches of mercury right here on average. It's pulling, it's pulling, it's pulling. We got about 3 inches of mercury. Then right here, where the intake valve is supposed to open, when it's supposed to open and it doesn't, the manifold vacuum suffers because this piston is not contributing to the intake manifold, right? Doesn't this waveform tell the story? We got low compression because the cylinder didn't fill. Why didn't the cylinder fill? Because the intake valve didn't open, and we got proof of it right here between this and the lack of vacuum in the manifold. Vacuum goes up, lack of vacuum goes down. Please raise your hand if you're with me so far. Awesome. So now let's go back to this question here. First of all, let me show you now listen, cylinder number 2, let me go back to this picture right here. Cylinder number 2 is right here. Here's cylinder number 2, cylinder number 4, and cylinder number 6. 1, 3, and 5 are in the back. Doesn't it make sense that I'm going to be taking off only this valve cover? We've got, you know, I'm going to loosen this bracket so I can gain access to the fasteners, but I've got a little 8mm bolt here, and one here, and one here, and one here. Is there any reason to pull off everything? Right? We just want to get to that. We just want to get to that rocker. How do I know that? Because the waveform tells me the entire story. I know my intake valve is not opening. I don't know if the cam lobe is gone. I don't know if maybe the push rod vanished into thin air, right? But I do know these are common for the threads for the rocker pedestal to rip out of the head. But either way, I know if step 1 is going to pull that valve cover off and take a look. So that's what I did here. And if you look closely, you can see that this bolt right here that passes through this rocker assembly and onto this pedestal, the threads ripped out. Somebody over-torqued this and the threads came right out. So all I had to do was do a thread repair, a time cert on this, or helicoil, and restore the threads, and I got this car back on the road in less than an hour. But let's go back and answer this question. What about this right here? Why did this occur? Let's talk about that for a second. Let me see if I can zoom in on this. Let's talk about this. Here, cylinder number 2 did not contribute to the intake manifold. We know that because the intake valve didn't open. Why did vacuum get so intense successively here? The question I have to ask is, what is cylinder number 2 doing in this area right here, between here and here? Let's follow along. So here's cylinder number 2. Cylinder number 2 begins its compression stroke. Let's go back to that relative compression test, that sound we heard with our ears. Forget the amp probe for a moment. What did we hear with our ears? We heard a variation in what? Of load, but what happened to the speed of the crankshaft? The speed of the crankshaft increased as cylinder number 2 completed its compression stroke. So from here to about here, the crankshaft increased in speed. So if I'm creating vacuum here, let's pretend I put a gauge on this. If I'm inhaling air, if I pull slow enough, that gauge won't move. If I pull faster, I will start to build a vacuum. If I pull down rapidly, the vacuum gauge is going to go way high, right? It's the same reason if you measure vacuum at idle on a healthy engine, you might see something like 21 inches of vacuum or 19 inches of vacuum. But if you hold it at 2,000 RPM steadily, vacuum increases to 22 inches of mercury or more. Why? Because the speed of the engine allows for a stronger vacuum to build inside the manifold as we consume more air. So here the engine is picking up speed between here and here. Vacuum is starting to intensify in the manifold. And then you got to ask the question, how come vacuum depleted right here? Well, the next cylinder in the firing order, not cylinder number 2, but the following cylinder, cylinder number 3, that is starting its compression stroke here and finishing it here. Cylinder number 3 has nothing wrong with it. It has integrity, meaning it's going to load the starter, it's going to load the crankshaft, load the piston, and it's going to slow the crankshaft down. And if we slow the crankshaft down, vacuum is going to subside a little bit. Please raise your hand if you're with me. Excellent. Now, again, vacuum goes up when a piston contributes. So we've got a contribution, a contribution, a contribution. And although overall manifold vacuum dropped for a moment because the engine slowed down, number 6 is still contributing, and so is number 1. And so is number 3, but number 2 is not. So I hope that makes sense. It drops way down here because the manifold suffers for one full stroke, one full contribution for number 2. And then number 3 picks up where number 2 left off. I should say where number 1 left off. And the manifold vacuum starts to increase again. And it's going to drop off every time cylinder number 2 is supposed to contribute, but cannot. So I hope that makes sense. Oops. I hope that makes sense to you. So I know I've taken this extra slow, and we spent some time on this, but I want you to understand that this is a very easy to understand case study. And it's the building blocks to support what's to come here in this class in the next successive case studies. My point is I took the long way around. I purposely grabbed data from here, and I grabbed data from there. And if you go back, I even grabbed data from the, oops, I think I'm going the wrong way. I even grabbed data from the tailpipe. We're not using it here. I chose not to use it. There's information there, but I chose not to use it. But it's there if I wanted to learn from it. And I did, believe me, there's information, valuable information in this tailpipe waveform. I know it looks like a bunch of squiggly lines, but there's good information there. But we're not going to talk about that yet. We're going to talk about that later on because we're going to go through these building blocks. We're going to learn as we go.
Real quick, can you go back to that end cylinder?
Yes.
For me, Brandon? We had one question, and you've clearly answered it, but I think something that came to mind just now, you spent a lot of time on that syringe, which is brilliant with kind of expressing and showing why we would have uneven pockets during leaks. But I think the same could be done here, right? Like if you were to take that syringe at top dead center compression and the exhaust, the exhaust valve just closed, right. So your finger's on the end.
Yep, so kind of gone off on the exhaust stroke. Everything's open to the exhaust manifold. The exhaust is supposed to stay open when the intake valve opens, right? And the piston starts to descend just a little bit, and then the exhaust valve closes. So we've got just a little bit of air trapped in there.
A
So
little bit of air, and the intake valve doesn't open, like in this case. So you pull down to
So
bottom
we
dead
pull
center.
down and build a vacuum in the cylinder, and it looks like we've got about
deep
negative
vacuum.
12. Yeah, like 22 inches of mercury. And then we go back up on the compression stroke. So if you look closely, that much air is trapped in there from the exhaust during what would be overlap, right? We have overlap. Even though the intake valve didn't open, the exhaust is still open. So watch this. If I squeeze my syringe, I can build a little bit of pressure. I don't know what, maybe 12 PSI?
12 PSI.
Right?
But I think that just dawned on me. It's the same exact thing, but opposite. Like, you're expressing it at bottom dead center. We should start with the same or end up with the same that we started with. The same applies when you don't have an intake valve open. You're going to start with almost the same you're going to end with the same as you started with, which is nearly atmosphere, just a little bit more.
Yeah. Yep. That's perfect. And that's why this works so well, because when you have these confusing moments, something you can't, right? We can't climb inside the engine and watch this happen, but you've got an engine right here.
Yeah.
So if you can say to yourself, I'm on the exhaust stroke, my exhaust valve remains open. I'm supposed to open my intake valve, but I can't, right? But since my exhaust valve is open and the piston starts to descend, I close the exhaust valve. I should be on my induction stroke, but I can't get any air in. I go back up on compression and I build about 12 PSI. Right there.
A little bit. And the other thing, the giant curve there is a big indicator. It's usually obvious once you get some experience, but maybe early on you forgot, what we talked about that big old curve. Look at the pressure. There's no way an engine is going to create that kind of negative pressure in the manifold.
Right. What we have here in this area, this is 10 PSI negative. So down here is about 14, which means this is about 12 PSI negative. And pardon my chicken scratch. This is really hard to do with a mouse. So here is about minus 12 PSI, which is about 22 inches of mercury, okay? Which is not crazy, right, for manifold vacuum on a good engine. But the point is, if I get rid of this ink, give me 1 second here. For some reason, it works better if I talk myself through it while I'm trying to get it to happen. There we go. This intake valve should have opened here, and this should drop relatively straight down, and this should stay flat as the piston contributes to the open intake manifold, and then it should slam shut, and we should start building compression again. That's not what happened here. If I had a pressure transducer screwed into the syringe and I drew down with it sealed, vacuum is going to strengthen over time till I get to bottom dead center, and then it's going to change direction. The vacuum will dissipate, and once we reach atmospheric, it will turn to pressure once we cross that threshold of 0 PSI. So the significance of the rounding is the piston descending and then ascending against closed valves.
It does say running there. Okay.
Yeah, this is running. The engine started and it's running. So I hope that makes sense. Now, I want to move on to the next one here. And this next one is a 99 Cadillac Deville. Now, this was pretty neat. This one came in, it's got an excessive blow-by here. That's the root cause of the failure. But we're gonna pursue the clues given us by the engine. And again, this analysis, part of it is gathering the information with the scope. And a lot of it is assembling all the puzzle pieces to come up with a logical answer, to eliminate what simply cannot be. That's what I like to do. So what we have here with this Cadillac is the vehicle showed up to the shop with the check engine light flashing. It had a P0306 indicating cylinder number 6 had a misfire present. I performed a relative compression test, just like I always do. And I had no audible indicator or visual indicator on my lab scope that there was a significant loss in compression, meaning all 8 cylinders loaded the starter relatively similar to one another. So in my mind, doesn't that kind of initially rule out an engine mechanical fault? Please raise your hand if you agree. I didn't say it's not mechanically faulted, I said, I'm probably not going to go into that engine mechanical funnel first. Does that make sense? So obviously, we always want to keep in mind the cost of the repair. Now, this old sow is 20 years old, right? And I'm not here to bash any cars, but it is what it is. And if there's anything involved within this engine, it's highly unlikely we're going to be disassembling it for repair. But let's pretend this is just outside of factory warranty, right? This is a newer vehicle, and it's not quite under warranty, but certainly fixable, meaning it doesn't exceed the value of the car. Let's just pretend that for a moment, because sometimes we have to make decisions like that. So again, my initial approach is to do the tests that are going to give me the most information, right, for the least amount of time or energy invested. But the one thing many technicians do not ask themselves, do not factor in when doing tests is they get a diagnostic routine going, right, and they get comfortable with that diagnostic routine, and they try to apply that same routine to every car. And that doesn't always work. A lot of times it consumes a lot of information. Let's pretend one of your go-to tests was a fuel pressure test. How many cars do not support a Schrader valve, easy access to the fuel rail, right? Some of them don't even have pressure sensors where you can get usable data from a scan tool. So doing a fuel pressure test on one car might be a couple of seconds to perform, but on another car, it might not be even possible. It wouldn't make sense to do it. So I always create a game plan around the car I'm working on. Some of the questions I ask myself are, what is the capability of the scan tool I have at my disposal? How is the ignition system configured? Am I doing with a 2-wire cop coil where I can get right on the primary wire? What if it's a 3-wire cop coil and I can't get on the primary with a voltage lead? Maybe I can look at coil current, but I can't see combustion through the eyes of the ignition scope because I can't see that primary. I can always couple to it capacitively, right, with one of those paddles. But what if we're dealing with like a Honda or a Toyota where there's lots of nickel shielding in the coil and gathering a usable waveform can be a nightmare, right? Maybe I can pull the cop coil out and put a high tension lead in there. Maybe not. What sort of fueling strategy does this car have? Does it have a mass airflow system where it weighs the air directly to determine fuel injector pulse width? Or maybe it uses a map sensor by way of a speed density inferred value. So all these things come into mind. What about engine configuration? You know, am I working on a V10 Audi where the whole thing's shoved under the dashboard and you can't get your hands anywhere? Or is this a big open 1.6 liter Honda where you can crawl in the engine compartment and sleep with it? You know what I mean? These are things that come into mind when I decide what tests I'm going to implement on the car I'm working on. And sometimes it just means taking a breath, backing up, and analyzing what's in front of you before you commit to working on the car. But the best approach is always going to be the one that gives you the most diagnostic information for the smallest amount of time or energy invested. And this, of course, is going to increase our efficiency and also lower the cost to the customer as well. So considering what this car is, this car, I think this one had cop coils. Even if it didn't, if it had waste spark, I can't recall now. I chose to analyze secondary ignition, whether I pulled the coil out and interfaced a high tension lead in between the coil and the top of the spark plug. Secondary ignition, because of how big this engine is and how it's tucked into this engine compartment, it just made the most sense for me. It gave me the most bang for my buck, right? The little amount of time invested, and gave me a lot of information because I am quite comfortable with ignition analysis. I learned that to be a very basic test, and it applies to almost everything out there. So why not master it? Now, anybody that recognizes ignition waveforms will see that spark discharge, I've got about 10,000 volts here, 10 kV, meaning my coil was able to saturate, right, take on energy and build a magnetic field. It was able to collapse and induce a voltage through that step-up transformer that ignition coil is. And there was enough energy to overcome secondary resistance to create 10,000 volts. But shortly thereafter, this voltage dissipated to ground. So that tells me quite simply that there's a short. This spark is not firing across the spark plug gap as it should. It's finding a path to ground elsewhere. So what's the next step? Let's pretend this is a cop coil and I've got it out of the cylinder head, right? It's not touching metal. And I've got a wire that goes directly from this cop coil to the top of the spark plug. Clearly, there's no short to ground externally. What am I going to remove at this point? Where am I looking next for a short to ground on one cylinder? I'm going to pull the spark plug out. It just makes sense. So I pulled the spark plug out, and this is what I found. Lots of fouling here. This thing was using some coolant, but a lot of oil was burning. So what questions do I have? Could I have oil getting past the valve train? Meaning maybe I've got a worn valve guide, right? And oil is getting past the guide and past the seal. Maybe there's nothing wrong with the guide at all. Maybe the seal is just old and dried out, and it can't scrape the oil from that valve stem, right? I've got dried out valve guide seals. Could I also have stuck oil rings, right? Could I have a crack in a piston or something like that when oil's getting up past, right? Luis Fraga said, maybe the customer never changed the spark plug. It's possible, but on any spark plug, is that type of fouling normal? Is that healthy? That's not good at all. So we're going to pursue an oil consumption issue on one cylinder. So those are the questions I have to ask. Now, let's think about the data I already know. What did my relative compression test tell me? It told me I have compression in this cylinder that is relatively similar to the other 7. So I assumed right away I didn't have a mechanical fault, but I think it's safe to say I don't have a loss of compression. So what does it say about my compression rings or a crack in a piston? Doesn't it indicate that's probably unlikely? Now, I could have maybe just stuck gunked up oil rings, right? The oil scraper ring that channels the oil away from the cylinder walls and pushes it through the piston back into the crankcase. That could be a case, right? I could also have valve train issues. So again, pretend this engine is in a range where we can adequately repair the engine, right? If we had to send a cylinder head out, it would be well worth doing that job. But if it meant replacing the engine or servicing the low end of the engine, would be too expensive and not justifiable, and the customer would get rid of the car. I'd like to know before I go any further. So what test can I perform that could help infer whether my problem is down low, meaning stuck oil rings, or up top, a worn valve guide or dried out valve guide seals? A wet compression test, right, Nathan? But I didn't have low compression, did I? And I found in every engine, if I put a little bit of oil, even if I have a good cylinder, it improves compression, right? Chip, please specify. Chip Vickery mentioned that I could look on the dipstick tube. What would I be looking for? He's absolutely right. Think about this. If I had compression, if I had oil getting past oil ring, couldn't I also have compression going past the oil ring? Even if it's a little bit, maybe not enough to affect start or load, but certainly more so than the other cylinders. Wouldn't I expect to see pressure in the crankcase increase? Maybe if it isn't even drastic, maybe more so than the other cylinders. I think that's a valid test. So what I'm going to do now is I'm going to take my pressure transducer and I'm going to put it on the engine somewhere right down here where the dipstick tube is. And I could use a delta sensor, right? The delta sensor reflects change very easily. So we're not looking for a huge change in pressure as far as pressure goes, right? And as far as amplitude goes, a pressure value. But I do want to look at the delta sensor because it could show me a rapid change in pressure. In this case, I'm using the ATS inches of water sensor, which kind of works very similarly. I'm going to couple those two to my lap scope, and I'm also going to implement an ignition sync. What's the sync going to tell me? The sync is going to tell me when whichever cylinder I choose, I'm going to go with ignition number 6 because that's my suspect cylinder. It's going to tell me number 6 is on top dead center. So here, my ignition coil command for cylinder number 6, my inches of water sensor on the dipstick tube, and I'm going to crank the engine over. Now,
Question real quick, Brandon.
please,
Simon
what do
just
you,
asked, do you recommend isolating the intake? I imagine him when doing a crankcase reading.
you mean from the PCV system? Is that what you mean?
I would imagine that's what he's referring to.
I don't feel it necessary. For one, how many PCV systems are built directly into the intake manifold by way of a fixed orifice where you can't really alter them? Or look at some of your Euros when you have that big, expensive, everything's all up integrated into the valve cover. I don't even think you're capable of separating, you know what I mean, quite easily. So I don't bother because we're looking for change. The point is, one of these one of the 8 cylinders is not going to be like the other. I want to see, is it going into the crankcase or is it not going to the crankcase? So I should still see a difference. So here, the way this scope plots data is it automatically scales the scope screen by itself. Not every scope does that, but no worries. I have an ignition sink in number 6 right here. And in red is my crankcase pressure by way of my inches of water transducer. So what we have here is once I start, we're at 0 PSI, right, atmospheric. When I start cranking the engine, the overall vacuum, the overall pressure in the crankcase begins to drop into a negative state of vacuum. Why? Because cranking manifold vacuum is being introduced to the crankcase by way of our PCV system. Totally normal. And we are interested in this activity right here and how it relates to cylinder number 6. So what I'm going to do is I'm going to take these 2 waveforms and I'm going to line them up to overlay one another. Bear with me one moment. So we see we've achieved 1.6 inches of water. Okay, not that that matters, but I'm telling you the pressure transducer is of an absolute characteristic. So it's going to display the inches of water, the negative pressure inside the crankcase. And I see these pressure spikes here. Is that normal? I don't know. It might be. We got to see how it relates to the ignition events because this tells us the engine cycles. If I see a spike like this, if I see 7 of these spikes fall in one cycle or 8 of these spikes fall in one cycle, I'm going to say those spikes are normal. If I see one of those spikes in the engine cycle, I'm going to assume it relates to one cylinder. So I'm going to squish these 2 together and see how they overlay. And what we have here is, if you look closely, we've got that overall manifold vacuum entering the crankcase, and we've got pull and a pull and a pull, and all of a sudden, a pressure spike. And then vacuum inside the crankcase starts to recover, and then a pressure spike. So we've got about seven little pulses and then a big pulse. And that big pulse occurs every time cylinder number 6, our suspect cylinder, approaches top dead center compression. How do I know it's top dead center compression? Because that's the ignition strike. It fires close to TDC. So what is wrong with this car? Is my problem up top in the cylinder head in the valve train, or is my problem down low in the crankcase? My problem's down low. I've got blow by. So in just a couple of minutes, I've actually spent more time talking about this with you than it took me to analyze this vehicle. So here's the best part. I know it's going down low. I know that's where the oil is coming from past the rings. But I also know my compression is relatively similar to the other cylinders. So in my mind, it's probably not a crack in a piston or a broken ring. It's a stuck oil ring. So I could do a couple of things. Maybe I can treat this with a chemical and try to get it to loosen up. But what the customer's concern is to make the misfire go away. Why? Because he's going to drive right down the street to the Cadillac dealer. He's going to trade it in. He's going to get himself a brand new Cadillac. So all I did was replace the spark plug to get rid of the misfire. If I put in a spark plug that was not fouled, the engine began to run normally. When I say normal, I mean it performed normal. It's still going to be consuming some engine oil over time. It might go another 10,000 miles before the misfire returns. I don't know. But the point is, the customer wanted just the spark plug replaced. And now that the car is in good working condition, seemingly working condition, it's far easier to trade in at a higher value than it is with a misfiring cylinder. So I hope you can see how it's the tools that we used and the logic involved by putting the puzzle pieces together. using the relative compression test to rule out an engine mechanical fault initially, but that same test proved that I don't have a broken piston, a crack in a piston, a broken ringland, a scored cylinder wall, right? It almost inferred that the rings were stuck, the oil ring at least. So are there any pertinent questions that have to be answered now, Brent, or can we move on to the next case study?
Stuart asks, if it wasn't in a crankcase, how would you prove a dried valve stem or worn guide?
I don't think you could, but you could rule out blowing past the crankcase. Now, I'll be honest with you. Let's pretend those spikes in the crankcase were all relatively similar. It still doesn't really prove the rings aren't stuck. But I do have positive confirmation in this instance that the rings were stuck because of the compression. So I hope that makes sense. That's the best way I can answer your question. This stuff isn't crystal ball magic. It's just putting the puzzle pieces together.
Yeah.
Does that make sense?
Yeah, I think we're good.
Okay.
We have got questions, but I think they're better to try to get at the end here.
Okay, great. This next one here was a lot of fun. This was a 2014 Chevy Equinox with a 4-cylinder engine. And the car came in, I'm going to call suspected catastrophic damage. I'm going to tell you guys a story here. Customer's been driving this car around with absolutely no problems whatsoever. This particular morning, it was minus 18 degrees with the wind chill in my locale. So the gentleman woke up, he jumped in the car and started it in the morning, let it warm up while he drank his coffee. He got in the car and started to drive to work, to get started on his day. Shortly after leaving his home, he began to smell an odor. And then he started to see some smoke from underneath the vehicle, behind the vehicle. Shortly thereafter, the car started to perform poorly and then eventually got a check engine light to come on. He decided at that point it was time to come to the shop now, right? Bail out on work today and get this car taken care of now. So as he made it into the parking lot of the shop, this thing was banging and carrying on from underneath the hood, and he shut the car off. Brought the car into us. It was explained to me just like I explained to you what the problem was. Well, I went out to the car in the parking lot. I smelled what smelled like burning oil. I saw some smoke. When I hit the key, clank, 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 this thing sounded like it was going to explode. So immediately I prepared this customer for engine replacement. Right? We got to get this car in and we got to do our diligence and check it out for sure. But I told him it was safe for him to go home, get a ride home. I'm like, look, it's going to be a while. You probably need an engine. We're gonna figure out what needs to be done to rectify the situation, and we're gonna call you with a price estimate. So I decided it was a nice slow day. Nobody's leaving their house. It was 18 below zero. I'm going to hook up my pressure transducers and see this catastrophic failure live and in color, if that makes sense. I mean, I was excited about this. So I pulled off the ductwork here, the air box and the inlet snorkel to introduce my pressure transducer. It's funny, when I took it off and went like this, I got a bath. I got, my clothes got all wet. Here, if you look closely, I've got my vacuum transducer connected to the intake manifold, the PCV system, the evaporative emissions purge hose. And over here, I've got my inches of water transducer. This serves as a delta sensor on my dipstick tube. So I'm just going to crank the engine over and gather some data. Now what you see here is a zoomed in capture of the in-cylinder cranking compression waveform. Now if you look closely here, what you'll see is a whopping 2 PSI, 2 pounds per square inch of in-cylinder pressure. And I thought to myself, what the heck? This thing's got to be terrible. So this would be our expansion stroke, right? We go back our exhaust pocket, and we've got about minus 12 PSI, which is about 24 or more inches of vacuum. And then we see that vacuum dissipate. We know this area right here is our exhaust valve opening. That seems to be occurring at about not 30 degrees, but maybe 60 degrees before bottom dead center. This would be our exhaust stroke here, right? Very little pressure because we're cranking the engine over. And right here, the 360 mark is where the piston starts to come down and the intake valve should open up. So if the intake valve should open up, should I be pulling vacuum in my cylinder as my piston descends? If the intake valve is open? Very little, right? My piston should be inhaling. There shouldn't be any restriction. So if I got any vacuum in there, it should be cranking vacuum, maybe 1 or 2 inches of mercury. That's a fair number, right, Brent? Cranking vacuum. But here, what do we see here? We don't see 1 or 2. We see about 7 inches of vacuum. Excuse me, 7 psi negative, which is about 14 inches of vacuum. And then suddenly it disappears. I don't know what's going on yet. But then I come over here, and this is the rest of my intake stroke from here to here. And I've got pocket differential between here and here of about not 2 or 3 psi differential. We've got like 12 or 13 psi differential. And you could clearly see leaning towers here. So this is substantial. So here is top dead center 0 degrees, bottom dead center 180, top dead center 360, bottom dead center 540. At this point right here, my piston should start changing direction. And we know our intake valve closes at about 55, maybe 60 degrees after bottom dead center. So here's 30, and here's 60. I'm going to zoom in a little bit. Here's 30, and here's 60. This is where the intake valve should close, and we should start building compression. But we don't. Here's 90. Here's 120. Here's 150, and we still don't start building compression. No, we're at about 170 degrees after bottom dead center did we start to build compression. So let's think about this for a moment. This represents 180 degrees of crankshaft rotation. This would be 90 degrees. Halfway between that and the bottom is about 45. Right? Halfway between here and 90 is about 60. So here is where we are supposed to close the intake valve. And we have this much stroke, about 120 degrees to capitalize and build compression. However, if we go back to my PowerPoint, we don't close it here, do we? We don't close it at 60 or 90 or 120 or even 150. We close it about 170. So if this represents 180 degrees of crankshaft rotation, and there's 90, and there's 120, and there's 150, and there's 170, how much stroke do I have to build compression? How much pressure can I build by moving the piston that much? It looks to be about 2 psi here. So now it hits me like a ton of bricks. I said, holy smoke. I don't have low compression because I got this huge hole in this combustion chamber. I have low compression because my intake valve is extremely late, at least on this cylinder, right? It's supposed to close over here, and it's closing way over here. And on top of that, if I had a hole in this combustion chamber, right, I have a bent valve and it won't seal, am I going to pull minus 13 psi, 24, 25 inches of vacuum in the cylinder? Am I going to pull a vacuum if I got a hole in there? There's no way in heck that's going to happen. So now I'm getting excited. I think I'm onto something here. Maybe this isn't as bad as I think. So we're going to pursue it further. Now we've got other data to look at, right? I captured from the intake manifold and I captured from the crankcase. Let's take a look at that stuff and see what we see. Maybe we have some more puzzle pieces that we can assemble. So what you see here in green is my vacuum transducer on the intake manifold as I'm cranking the engine over. Okay? And compression in yellow. What I'm going to do here is I'm going to come over here and I'm going to turn off the yellow trace. And I'm only going to leave the green trace on, and I'm going to take a zoom box, and I'm just going to put a box around it to zoom way in and stretch it out. And what we see here, vacuum makes the trace go north. And I'm zoomed way in. As you can see, this is 0, and all the way up here is still less than 2 psi positive. So we're zoomed way tight. These look like variable, huge variations from contribution to contribution, but we're talking very little. I'm just zoomed in. So I've got a vacuum pull, a vacuum pull, a vacuum pull, and a vacuum pole, and the process repeats itself again. 4 vacuum poles, and they're all relatively the same. What that means to me is this. If I've got one cylinder that looks like this, and all the vacuum poles are relatively similar, doesn't it infer the other cylinders, if I go in cylinder, should look the same? Would you agree with that statement? Please raise your hand if you agree with that statement. That's what I see in this. I see 4 equal contributions to the intake manifold, and I only physically looked in cylinder at one of them. If this one produced a vacuum trace, the other 4 produced the same vacuum trace, the other 4 in cylinder captured should look relatively the same, meaning I don't have one cylinder that has shifted timing. I've got an entire engine, meaning I've got a timing issue. That's what I see here. So there's one last thing. I hear all this noise. I got this catastrophic engine failure. There's oil all over the place. Maybe I pushed a piston through a block. Unlikely, but let's just take a look down low. This is the dipstick tube. I don't know what it's supposed to look like, but we've got up and down variations of about 2 inches of water. Would you agree that they all about look similar to one another? Please raise your hands if you do. So right away, I think I just have a timing issue, and I do not have catastrophic engine failure. In fact, my low compression is simply because my extremely, extremely, extremely late intake camshaft timing. So putting the puzzle pieces together, I put the car up in the air. We don't have to see all this. I just said all that. I put the car up in the air, and I saw oil. I wanted to know where that oil was coming from. I thought I had a hole in a block. I put the car up in the air, and I saw the oil was coming from between the transmission and the engine in the bell housing. I got a borescope up there, and I saw that the rear main crankshaft seal was pushed out of its bore. It was displaced. I said, how the heck could that happen? And then I remembered it was 18 degrees below zero. I don't know what that is in centigrade or Celsius for you Euro guys or guys in Australia. It's cold. It's cold. It was 18 degrees below zero with the wind chill. And remember, when I took that air box off, I got a bath. What was ice is now water. The PCV breather system was frozen in this car. And if the crankcase can't breathe, pressure starts to build in the crankcase till it overcomes its weakest link. In this case, it was the rear main seal. When the rear main seal popped out, oil began to drip. That's where the smoke and the odor came from. When enough oil came out of this vehicle and the VVC system couldn't function properly, we set a check engine light. When enough oil came out that the timing chain starved for oil and stretched, it jumped 120 degrees. And that was the noise we were hearing, that catastrophic noise. So I wanted to make a tough call. I said, you know what? Maybe if we retime this engine, we could save it. But then I remembered that it lost oil pressure, and we don't know the inside of this engine, its condition. So I think, and I'm sure you'll agree with me, the logical, the most safe approach would be to recommend a replacement engine. And that's what we did. But just to verify, I looked down inside all the combustion chambers with a borescope and proved that there was no valve collision. Lots of times, you know, if we lose time, specifically on the intake cam, it's very easy for the pistons to come in contact with the valves, but that didn't happen. So we did put an engine in this, but again, I think if we retimed it, it would have started and ran, at least for a little bit. I don't know. So I hope if you're with me on that one, okay? I don't want to spend too much more time on that. The rest would just be storytelling. But I want to move on to another case study here. Now, this one here is kind of funny because I learned my lesson the hard way, and I want you guys to learn the same lesson, but I want you to learn it here. And I learned the lesson because I reflected upon the data I captured. After I made a mistake, I went back and reviewed the data once I already knew the final outcome. And then I learned something from the data, and I will never, ever make that mistake again. So I want to see if you guys are with me on this one. Now, as soon as I tell you it's an 03 Jeep with a 3.7 liter engine, you guys probably already know what's wrong with it, and you'll want to move on to the next case study. This one lost an exhaust rocker. It spit one out. But we're going to go through the data because the data tells us a lot. So the customer's driving the car down the road, and for no apparent reason, bang, the thing instantly starts misfiring. There was no performance issue leading up to this. It was fine, and then it wasn't. So I want to get into a diagnostic funnel as fast as possible. I noticed cranking the engine that there was a disturbance in the cranking cadence. Notice I didn't say dead hole. This didn't make that same sound that Bryn said, that da-da-da-da, da-da-da-da. It didn't sound like the engine picked up speed. Actually, it kind of sounded like it did something different. It went da-da-da-da, da-da-da-da-da, like there was a pause. So I describe it as a hiccup. I don't know what else, but I do know it's mechanical in nature because I could hear it with my ears. So of course, I'm going to perform a relative compression test because I want to see what cylinder is to blame. So I'm using an amp probe. Again, I have an ignition sync. This time I'm on cylinder number 1, and the firing order that I researched is 165432. Now I'm sure you guys will agree, 1 and 6 look very similar to 432, but number 5 is significantly higher. So here's where my mind was. If number 5, if a low peak represents low starter load, a high peak represents what? Represents high starter load. What causes high starter load? Higher compression, right? Let's talk about some things. Could I have ingested oil or coolant in that cylinder? Is that a possibility? It is a possibility. How long would that situation last? Cranking the engine over? Probably 1 cycle, right? As soon as the exhaust valve opened and we pushed that oil or that coolant out the exhaust port, if I was filling a cylinder fast enough that the next cycle experienced the same thing, we'd have some symptoms leading up to this, right? We'd have steam coming out the exhaust. We'd probably have coolant dripping out the tailpipe. And certainly we'd have a dead miss at all times. It didn't just happen instantaneously. So oil or coolant filling the cylinder, like a hydrolock situation, is probably unlikely. Well, what about carbon? Could carbon increase compression ratio? That could happen. But again, if I had enough carbon building on top of a piston to change the load on the starter by more than twice, we would have a significant running problem to build that much carbon. Would you guys agree with that? Please raise your hand. So just using logic alone, we probably don't have an oil, a coolant, a dripping injector. We probably don't have a carbon issue. It's probably mechanical in nature. So moving on, I'm going to implement another test that will help yield me another answer. I truly don't know at this point why, because I never saw this before. I never tested in this realm. I never tested using a relative compression test while I had this problem. So I decided to move on to the cranking intake test. And what we have here is vacuum going up, and then all of a sudden, not only a decrease in vacuum, but we crossed the 0 threshold. We built pressure in the intake manifold. And then it recovered. We got vacuum pull, a vacuum pull, and a vacuum pull. So the firing order is 1, 6, 5, 4, 3, 2, and there's 1 again, according to our ignition sync. I have channel 2 turned off. That's why you can't see the ignition sync. But you have to understand it's there. So I thought to myself, number 5 is pushing pressure into the intake manifold. I go back to my relative compression test and it shows number 5 is my problem. Isn't that what this indicates to you? Isn't it what this indicates to you? Looking at this test, wouldn't you say number 5 has the tall RC peak, relative compression peak? I would. And then I lean on my intake trace to figure this out. And I say, yep, number 5 is definitely my problem because when the intake valve opens for number 5, all my pressure dumps into the intake manifold. So what do? I go over to bank 1, where cylinder number 5 is housed, and I pull the valve cover off, and I go to find my rocker, and guess what? There's no problem there. So I did what every good tech does. I turned around to see who's watching to see me botch the test, and no one was looking, thank God. So I put the engine cover back on, and then I went over to the other side, and I pulled the rocker cover off, and I saw it was cylinder number 2 that had the problem. So then I stepped back and I said, okay, obviously it's number 2 that's the problem. I could see visibly with my eyes that the rocker came off. It's definitely number 2. But why the heck did my relative compression test tell me it was number 5? And why the heck did this cranking intake test show me cylinder number 5? Guys, this is going to happen to you. It's going to happen unless you take the time to understand from your mistakes. Don't blow over your mistakes and just throw the scope away and say, I don't know what the heck I'm doing. This test is dog crap. Use this information to learn from it. And I will never make this mistake again. I'll show you. Check this out. So after that, I realized on my intake trace, remember I told you this is cranking vacuum? 1, 6, 5, 4, 3, 2, the firing order. This is ignition sync number 1. Guys, where does the intake stroke start in the 720-degree engine cycle? Where does the intake stroke begin? Here's 0, here's 720. Where does intake stroke begin? The 360 mark. I think this is the intake pole for number 4. It's not. 165432 is the firing order. If I'm referencing the intake manifold and I use the same ignition sync, I got to move the firing order around 360 degrees. 165432. I got to do this. The firing order then becomes 432165. Even though I'm referencing ignition strike number 1, I got to tell myself it's number 4 to put myself out of phase. Does that make sense? Please raise your hand if you understand. Good. Now watch. So now I do the old switcheroo. I went from this right here, 165432, to this right here, 432165. Intake pull for number 4, intake pull for number 3. This should be intake pull for number 2, but it's not. It's this. You hear that? Do it again. Now I see it. Number 2 is definitely my problem. I still don't quite understand. Let's go in cylinder. Compression. We go on an expansion. Do I have an exhaust valve opening here? Yes or no? I do not. I have a rounded pocket. Further confirmation shows when I get down to bottom dead center and my piston starts to head north on the exhaust stroke, I build upwards of 140 PSI of pressure on the exhaust stroke. And then all of a sudden, the pressure disappears. What happened right here where that red arrow is? What happened? The intake valve opened. Listen, here's 140 PSI. Listen, where did that 140 PSI go when the intake valve opened? Where did it go? It went right here. It went to the intake manifold. Look at that. Listen, vacuum goes up, pressure goes down. Listen. Do you see how the waveform showed that rapid, sudden change in manifold pressure? It increased drastically. So I said, holy cow, now I know how I screwed up. This is going to seal the deal right here. Check this out. When I put the piston chart on here, look at this. Cylinder number 5, top dead center compression is where I saw my tall peak. That is also where cylinder number 2 is at top dead center of its exhaust stroke. But the exhaust valve didn't open. So I didn't have one cylinder on compression. Let me go back to this picture. Cylinder 5 was on compression and probably producing, we'll call it 180 PSI. But cylinder number 2 was on top dead center of the exhaust stroke at 150 PSI. That's not 1, but 2 cylinders loading the starter at the same time. So if I have 2 cylinders loading the starter at the same time, dang it, I was on a roll. If I have 2 cylinders loading the starter at the same time, I'm not going to have a compression peak showing 1 cylinder. I'm going to have double the starter load. Every time I see a high compression peak from this point forward, I never assume, in this case, it's number 5. It's probably the companion cylinder. Does that make sense? Please raise your hand if that makes sense. So now I tuck my tail firmly between my legs and I go over to the other side of the engine and I take the rocker cover off, not on this side of the engine, but on this side. And this is what I see for cylinder number 2. Do you see how the data in the, do you see how the evidence in the data captured not only proved what was wrong, it helped me learn from my mistakes. Always go back and review your data, even more stringently when you screw up, because that is what makes a great diagnostician, someone that learns from their mistakes and can now move forward more swiftly. I'm so thankful I screwed this car up, because if I didn't screw this up, I never would have learned this valuable lesson. And every time I see a tall peak, I never assume it's that cylinder. I always assume it's the companion cylinder. So I hope that makes sense. This is obviously a very easy find, right? But using new data acquisition, sometimes we get confused. But it's how we learn from our mistakes will help us become better technicians. Let's see what time we got here. Oh, man, we're running out of time. Guys, I am going to jump forward to, bear with me 1 second. I'm going to jump forward because all these are good, but there's ones on here that I really, really, really want you to see. How do I do this here? Oops. No, I don't want to do that. Uh-oh. Guys, bear with me 1 second. I'm going to stop sharing my screen. Bryn, sing something, will you?
Well, I can ask you some questions. Can you try doing two things at once?
Yeah, go ahead. Go ahead.
Can you use a low amp clamp like the one on the slide for relative compression?
You got to be careful, because those low amp clamps offer great resolution, but they max out. I think mine is a 60 amp. It maxes out at 60. Starters can easily pull, when cranking steadily, 150, 200 amps. Inrush exceeds sometimes 800 amps. So, that's not something you're going to want to do.
Yeah, I've heard of people doing it. They just use the calculations, obviously, as opposed to converting it to using it as a 60 amp clamp in their scope. But I've also heard that it could cause damage to it over time. But I know people have.
I would not doubt that at all. Okay, almost there, guys. I'm really sorry. Bear with me.
Yeah, no problem. We'll get through these questions. They're going to be asked anyways. If a relative compression is okay, is there still a need to do a pressure or in-cylinder testing?
Yes and no. If timing jumps, they're all still going to be the same, right? Let's say on a 4-cylinder engine. So we'll get to that. I can't fix this. What am I doing wrong?
Yeah, what Brandon's referring to, if it's a single bank engine and timing is off, then all of the cylinders obviously will be low in compression. So you'll see even peaks and valleys on that relative compression capture. But some rule of thumbs, as I mentioned, I think it was Monday night, 30 amps from the peak to valley is a kind of a minimum rule of thumb for gasoline engines, but also consider what the overall current is. Like Brandon just mentioned a moment ago, relative compression anywhere from 125 to, in some cases, close to 200 amps on a gasoline engine overall current. So if you have much lower, then you may have some cylinder timing issue on a single bank engine.
I got it.
There you go.
Back.
All right.
Can you see it?
I do.
Okay, good. So this next one here is a 2013 Honda Civic. This is the SI, the 2-liter. And anybody that's worked on them understands that, excuse me, the engine sits kind of underneath the cowl panel bit, so it's very hard to get to anything. Well, this customer that drives this car is a courier. This car is brand new at the time in 2013, but he already has 18,000 miles on it, and bang, the thing just failed on him suddenly. So he called me. We established a rapport, right? I'm the guy that works on his car. He said, I don't know what to do. So we had it towed in, and I hear a cranking cadence that exhibits one cylinder that's not quite like the rest. So I decided I'm going to do an RC test. I struggle to get the car inside. It barely runs. I mean, barely runs, but I got it in. Now, again, I can't get to anything very easily. So even more important for me to establish which direction I'm headed in before I take anything apart. So look, I'm using my trusty 20-year-old Modus. You can do it even on this. I've got a Delta transducer in blue connected to the intake manifold. I've got a yellow ignition sync on cylinder number 1. The firing order is 1342, and relative compression shows 134, 2, 134. Cylinder number 4 is my suspect cylinder. So the question I want to ask by looking at this intake trace is, how is cylinder number 4 affecting this intake trace? Remember that first Buick we did? We're going to ask similar questions. So what I'm going to do here is zoom in on one cycle. Okay? Now zoom in on one cycle. I know it looks terrible, but we can get past this. I've partitioned this 4 different ways. Why? Not because we're in cylinder, but this is a 4-cylinder engine. And I want to ask, here's cylinder number 4. How is it affecting the intake trace? So I want to look at all the induction strokes. Now we know number 4 is a dead hole. Please raise your hand if you agree with me that number 4 is my dead hole. Okay, good. Now I want to ask, why is it a dead hole? So the first thing I look at is the intake pole here in this first area. We got one pole, another one, and another one. Can number 4 create a pole? When the intake valve opens and the piston goes down on the induction stroke, are we seeing a pole here? It's a delta sensor. Aren't we seeing a pole? We are. So let's stop right there. If cylinder number 4 is a dead hole as it indicates here, and cylinder number 4 had a hole in the piston, are we going to create a pole on the intake manifold when it descends on its induction stroke? No. If it had a stuck open exhaust valve, are we going to create a pull on the intake manifold? No, not a nice deep pull. If I had a stuck open intake valve, could we still pull on the intake manifold? Yes. Why? Because the intake valve's open anyway during the induction stroke. So this pull right here does not prove it's the intake valve, but it certainly proves that there's no hole in the piston and it's not a stuck open exhaust valve. Please raise your hand if that makes sense, what I just said. Good. So we're not done yet. That is just one of 4 pieces of information on this capture. The second one, I ask, what's number 4 doing over here? It's on its induction stroke. The second question I ask is, what is number 4 doing in this section? Number 4 is on its compression stroke. Does everybody see that here? Please raise your hand. Number 4 is on its compression stroke between here and here. Number 2 is on its intake stroke. So number 2 is supposed to be pulling on the intake manifold. Bryn, I don't know about you. Do you see a pull?
No, I see it kind of plateau, yeah, for a second.
Yeah,
but
it kind of plateaus, but then I kind of see a what? I kind of see a push.
Yeah.
Right? Not a pull, but a push. So let's think about this. If number 2 is supposed to be pulling on the intake manifold, like number 4 is, we think number 4 might have an intake valve sealing issue, according to this area right here. Everybody raised their hand, so I'm sure they're in agreement with me, just putting the puzzle pieces together. Here, number 4 is on compression stroke. So if number 4 did have an intake valve sealing issue, doesn't it make sense that number 4, being on a compression stroke, could push some air back into the intake manifold? Please raise your hand if that's plausible. Okay, so this says cylinder number 4 is my problem cylinder. This kind of infers it's number 4 intake valve. And this kind of lines up and it's telling the same sob story. But we're not done yet. We still got 2 more pieces of data to analyze. Let's look at number 1. Number 1 goes on its induction stroke. It's supposed to pull on the intake manifold, and it does. Matter of fact, it pulls really good. Wouldn't you agree with that, Bryn?
Too good. It looks like
it pulls way low. So let's talk about this for a minute. We suspect number 4 has an intake valve sealing issue. What is number 4 doing in this area right here? Number 4 is on its power stroke or expansion stroke, right? Well, it's coming down on the power stroke. What are the valves supposed to be doing? The status of the intake and the exhaust valves on the power stroke. They're both supposed to be closed, right? But if the number 4 is descended on its power stroke and the intake valve is leaking, isn't it like being on another induction stroke? 2 pistons pulling on the intake manifold at the same time? That's going to cause like double the contribution. Isn't that kind of what we're seeing right here? Does that make sense? So this says number 4 is my problem cylinder. This kind of infers number 4 number 4 intake valve isn't sealing right. Excuse me. One moment. This infers number 4 intake valve isn't sealing right. This kind of infers the same thing. And so does this. How's your confidence right now? Honestly, how's your confidence right now? What are we going to find wrong with this engine when we take it apart? No matter how long it takes to disassemble, what are we going to find? Let's look at this last piece of information right here, since it's already on the screen. We got all this information with one 5-second cranking capture. Number 3 is on its induction stroke here. It's supposed to be contributing to the intake manifold. It looks like it's trying. Don't you agree, Brendan? It's trying to pull.
Yeah.
Question I got to ask is, what is number 4 doing? Number 4 is on its exhaust stroke, meaning the piston is heading up. The exhaust valve is supposed to be open. The intake valve is supposed to be closed, but we think it's open, right? We suspect number 4 intake valve is not sealing. So if number 4 intake valve is open and number 4 exhaust valve is open, isn't the intake manifold connected to the exhaust stream? So if number 3 is trying to pull on the intake manifold and the intake is connected to the exhaust stream, it can't possibly pull as hard as the intake manifold as it's supposed to, which would create a weak pull. This says number 4 is the bad cylinder. This says number 4 intake valve. 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 You guys know what we're going to find. So we take this engine apart. This is the intake side of the engine. This is the rocker shaft for the VTEC assembly that operates the intake valves. The camshaft sits on top of that. This is the exhaust side. We're going to zoom in on this area right here. This pin, you're not supposed to see that. That's supposed to be held inside this primary rocker by way of like a C-clip. Oil will come through here when it's directed to, by way of a solenoid, to pressurize this and shove this pin this way. And it will lock the primary and the secondary rockers together. The point is, this pin came out and got jammed up against this pedestal, and it held the intake valve off its seat. So the only thing I did was replace this assembly right here. I took the engine apart, slid that on, slapped it back together, and down the road we went. I've never, ever, ever, ever seen this problem happen before this or after this again. This is just a weird, usually on the Hondas, when something happens, it happens a lot, right? Their process is so exact. When they make a mistake, you usually see it often. I never saw this happen again. Man. Guys, I got a question to ask you. Ken, if you wouldn't mind chiming in, please, I want you guys to show a set of hands. Don't raise your hands yet. Ken, I want to ask you a question. I've got a really awesome case study that would just be absolutely phenomenal for these guys to see. But unfortunately, we're going to run out of time. So what I'm willing to do is one of a couple of things. Either I get through the case study and we answer questions afterwards, or we omit the questions and replace it with the case study. Or we just don't do the case study and we answer questions next 10 minutes. I'm fine with whatever you guys want to do. First, Ken, let me ask you, what do you think? You're the boss, man.
I think we can go ahead and do the case study and then take the questions. Everybody like to do that? Raise your hand.
Awesome.
There you go. So
okay,
let's do that.
We got 60 raised hands in about a half a second. So I'm okay with that. Good. I'm glad you guys are with me. I'm having fun. Are you guys having fun? This is great. I'm going to need another shower after this. All right, Brent, I need you to talk again because I got to go find that case study. It'll just take me a minute.
All right. Where were you on the intake? Where were you sampling?
On this engine, I always go to a common point on the intake, and that's a great question because I did this once on I went on the brake booster. I'm sorry, the purge hose. I went on a brake booster port once. And it was a 4-cylinder engine. I only saw 2 intake poles on that brake booster port. When I took the intake off, the brake booster port only went to intake runners 1 and 2. So that is not, you have to be weary of that.
Yeah. Purge is always referencing all cylinders. It has to.
Right. Or we'll have drivability symptoms, right?
Is the pulse sensor the same thing as a vacuum transducer? I'll answer that since you're kind of working in the background.
Yeah,
the pulse sensor is not the same thing as a vacuum transducer. The vacuum transducer, amongst the 3 main scopes that Brandon has brought up through this 8-hour session, ATS, Pico, and Snap-on, the ATS, Automotive Test Solutions, eScope, is the only company I know of that are using these vacuum transducers, but they're absolute pressure transducers. So they don't just change produce a voltage based off the change of pressure. It actually is an absolute sensor. It's different in the fact that voltage rises when pressure decreases and voltage falls or lowers when pressure increases.
Thanks, dude. Hey, are we back? Can you see?
We're back. Yep.
Awesome. Okay. So, all right. Oops. 1 second. I got to move something on my screen so I don't go nuts here. Bear with me. Okay. I've got a 2003 Ford F-250. You guys are going to wet your pants when you hear about this. This is funny. This came to me. I didn't do this one. This came from a really good friend of mine. His name's Dave Wagner out in the Philly area. Anybody who's been to Super Saturday, the ASA event in Pennsylvania, he's one of the masterminds behind it. So say hi to Dave. 03 Ford F-250. I still smile when I think about this thing. So this car has been around the block. This car has been to, you can see my screen, right, Brent? Okay.
Yep.
This car has been to like 4 or 5 shops over the course of the last 3 years. Now, it's got a, believe it or not, it has a misfire. It just has a misfire on cylinder number 3. Now, this thing has got new spark plugs. It's got all 8 cop coils replaced. It got a PCM. It got an engine harness, and then it had the cylinder head replaced. And when that didn't fix it, it got a whole new engine. And guess what? It still has a misfire in cylinder number 3. So Dave gets called into the shop to take a look at this thing. Actually, I think they brought it to his shop. It doesn't matter. But Dave has a game plan, right? He's not going to approach this vehicle with any prejudicial thoughts. It's just another car, right? It's just a car. So he's going to do the same thing that I've been trying to preach all along throughout this entire class. Gain as much information for a little amount of time invested as possible. So think about it. What the heck is a misfire? It's a lack of contribution from one cylinder as compared to the rest. We know if we don't have adequate ignition at the proper time, that could cause a misfire. We know if we don't have the right amount of air and fuel ratio, that can cause a misfire. And we also know if the engine can't squeeze the air or the cylinder can't squeeze the air right or get the air in the cylinder or out, it can't breathe right, we're going to have a misfire. So the relative compression test is typically something we rely on to give us that preliminary data. That's exactly what Dave did. So Dave implemented his, I don't know what this is. Is this an Autel scope, Brent? Do you recognize this?
Maybe it is because I don't.
Maybe Snap-on? I don't use this that often.
It could be Snap-on with the background inverted, I guess.
Yeah, that could be Snap-on. But tell you what, I don't care what scope I'm using. That's a relative compression test. I don't know which cylinder is which, but you know what? We don't need to know right now because they all look very similar. Now, I see one's a little bit lower than the others, but I certainly don't see something that indicates I have a dead hole here preliminarily. Do you?
Nothing obvious for sure.
Looks pretty great. So Dave, he's even more of a flat rate guy than I am, right? Dave doesn't even care that he doesn't have an ignition sync, or maybe he doesn't even know the firing order. It took him 10 seconds to put his amp probe around the battery cable and just hit the key. He saw all the cylinders were the same, so he said, you know what? I don't really care which one's cylinder number 3. It just doesn't matter. And sometimes that saves time to view things like that. But you learn to implement tests like this in time. So Dave, right off the top, said, I've got my engine mechanical funnel, I've got my ignition funnel, and I've got my air-fuel ratio funnel. It's probably not mechanical. Let's go look at ignition, and let's go look at fuel. Which one are we going to do first, Brent?
Whatever's the easiest to look at.
There you go. I don't know. It depends on what hood I opened up. All I can tell you is this is a Ford truck, and it's got fairly accessible 2-wire cop coils, meaning power goes into the coil, voltage supply, and the PCM is in charge of energizing the coil with the ground side. I got no problem with ignition analysis. I'm quite comfortable around it, and so is Dave. So he back probes cylinder number 3, ignition coil with a voltage trace, and he also put his amp probe around the coil's supply circuit so he can measure current through the circuit. Now, those of you that are familiar with Ford's multi-strike ignition strategy is something they do near idle. It's just a way to combat emissions. They fire the coil 3 times successively in this case. It's almost like having one long ignition event occur. But if you are familiar with this, you'll recognize that the current flow, what some would consider a shorted ignition coil, is not so. It's simply because the coil has been energized and discharged so many times repeatedly in such a short period of time, it didn't have time to fully dissipate before it charged again. It almost had a head start on the second charging event, the second dwell event, if that makes sense, that the way I described that. But what I see here consequently is I see roughly 100 volts on the primary side. You multiply that by 100, you usually get secondary. So that's about 10,000 volts or 10 kV. And I've got about a millisecond of time from this point to this point. So we've got maybe 1.5 milliseconds of burn time here. And I don't see that it's shorted. I see it's firing across the spark plug gap. If I had a burn through coil or a shorted spark plug or a weak coil, I would see it right here. Frankly, I'm not seeing anything. So right now, we don't think it's mechanical and we don't think it's ignition related. Please raise your hands if you agree with what I just said. Excellent. So we're thinking what? Probably fuel, right? So now we're going to go ahead and we're going to test the fuel system, or at least the fuel supply for this cylinder. So I got to tell you something. Again, Dave always takes the low-hanging fruit. If I had an injector problem, right? If I had an injector that failed to deliver fuel on one bank, what do you think would happen to the fuel trim on that bank? It'd be elevated, significantly elevated. Dave reflected upon scan data first, and he didn't see any elevated fuel trim, nothing to indicate that an injector failed to deliver fuel. But we're going to test it anyway. So what we see here is the voltage supplied to the injector. The injector is controlled on the ground side on this vehicle. It could be controlled on the voltage side, you know, like some older Ford trucks I've seen, like a Ford Ranger. What's that turbocharged one? I can't remember that engine. But here we can see this is 0 volts. It pulls darn near 0 volts, meaning all the voltage was used up on the injector side. And the fact that we have about 1 amp of current flow, maybe 900 milliamps of current flow, tells me we don't have a circuit problem. The fact that I see a pintle bump here tells me the solenoid, right, mechanically moved, it's shuttled. And the fact that our fuel trim is not elevated significantly tells me fuel sprayed. So I don't have an engine mechanical problem. I don't think I have an ignition problem. And I don't think I have a spark fueling problem. What did we miss? So Dave reflected upon the tests he did perform. And he said, I can conclusively eliminate fuel by way of fuel trim, the injector voltage trace, and current trace, along with the pintle bump. It's not fuel. He can prove it's not spark. But did he really, really prove that it's not mechanical by performing the relative compression test? What does that test tell us? It tells us a cylinder's ability to seal, right? To seal and to harness the air inside it. That's it. It does not say how the cylinder breathes. So Dave's going to commit to an in-cylinder running compression test, not because he has evidence that it's mechanical in nature, but because he has evidence that it's not fuel related and it is not ignition related. So he goes in cylinder and he captures this. Now, I know there is nothing on this capture to designate what the pressure values are. And there is no overlay present to designate or infer cam or valve timing. But there's something on here that just is not quite right. What do you guys see on here as being strange?
They're on it, man. You seeing the results there?
I'm seeing back pressure here. That's exactly what it is. I have no idea how much this is, but we know this should be laying relatively flat. So let's talk about back pressure. Could I have a restricted catalytic converter on this side of the engine? Could that cause back pressure? Just yes or no. Could back pressure be caused by a cat? It can. What tells me it's probably not a catalyst? How many cylinders are misfiring? Just one. If I had a restricted cat, wouldn't we expect, in this case, 4 cylinders, that entire bank to be misfiring? We would, right? So it's probably not a cat. Could I have advanced camshaft timing, meaning the exhaust valve closed early? That could certainly happen. Again, how many cylinders would that affect? It depends. If this was a push rod engine with one cam, it would affect both banks. If it's a camshaft on only one bank, like an overhead camshaft, it would affect all 4 cylinders. So again, we're down to 1 cylinder. So we're down to, could this be a cam lobe? Could this be a lifter issue? Let's check that out. That's certainly a possibility, right? Please raise your hand if it could be a cam lobe or a lifter issue. Definitely a possibility. Let's prove that out. So if I put some cursors on here, I'm going to compare to a known good cylinder, right? One right next door. The opening of the valve is signified by the change in pressure like we see right here. Uh-oh. Give me one moment. Like we see right here. This shows me where the exhaust valve opened. And on my suspect cylinder here, cylinder number 3, it doesn't happen at 30. It doesn't happen at 60 degrees before bottom dead center. It happens right in the middle, about 45. Let's go to a known good cylinder. It doesn't open at 60. It doesn't open at 30. It opens right in the middle, about 45. If I had a problem with a cam lobe or a problem with a lifter, I would see that reflected as a different point in the 760-degree rotation that EVO occurred. Does that make sense? It wouldn't happen here. Excuse me, this wouldn't happen here like it does here. It would happen earlier or later, depending on how that cam lobe metal was displaced. So this infers that it's not timing related or cam lobe or lifter related. So if it's not a cat and it's not a cam lobe and it's not a lifter, and we definitely know the cylinder could not exhale properly, what is in between those two? The manifold. That is the only thing that this could possibly be. Something is wrong with the manifold. I don't know what yet, but am I going to remove the manifold? Say yes. I'm going to remove the manifold and take a look. What did I see here? What did Dave see here? Excuse me. He saw carbon buildup. There's a bunch of welding slag in here from this aftermarket manifold that filled this port with carbon and did not allow the cylinder to breathe. Now let's think about this for a moment. It's not so much what Dave found. It's him following the evidence. We're going to touch on that in 2 seconds here. First, I want to state something here. How many times was this exhaust manifold off this engine already? At least twice, right? One for the cylinder head replacement and one for the engine replacement. Nobody think to look into this exhaust port to see. Nobody even just took a look out of curiosity to see if anything was in there. Heck, what if a bolt fell down in there or something? Or somebody shoved a rag in there for some reason and forgot to remove it. But it was Dave's thought process that figured it out. Think about this. The relative compression test, he only proved that the cylinder was able to seal and to squeeze. It did not prove breathability. The ignition waveforms conclusively proved the ignition system for that cylinder functioned properly and was not the source of the misfire. The injector waveforms conclusively proved that fueling was not an issue for this misfiring cylinder. It was the in-cylinder waveform that proved the cylinder could not exhale. It didn't say why. Not until he implemented his cursors and did some measuring. Logic told him it wasn't a camshaft because it only affected one cylinder. Logic also told him it wasn't a catalytic converter because it only affected one cylinder and not an entire bank. That and the measurement with the cursors proved that it couldn't possibly be a cam lobe or a lifter because that would affect duration, opening and closing points. It inferred definitely that his fault was between the cat and the valve ports, and the only thing in between was the manifold. So I don't know if I lost anybody on that. I think this one was very easy to see. And I think now is a really good time to take some more questions. What do you think, Brent?
Absolutely. I think this is more of a statement than a question, and I've tried to reach out, but I think this gentleman is gone. But Tom, if you're here, if it's a question, let me know. But he says on diesels, he uses a 600 amp clamp on only one battery, assuming both batteries are good. I think that's a statement. Next question, do you clamp off the PCV system while doing the vacuum readings? Earlier example on the Buick.
I don't. I never clamp off a hose. Maybe I will if I'm trying to experiment with something to see if there's a difference. But I like to leave the engine. I like to leave the car as it is. I try to disrupt it as little as possible for the same reason I don't open up. I don't feel a need to isolate the crankcase from the intake manifold because my delta sensor is going to show me change regardless, if that makes sense. On that note, I know lots of guys that will cap off the throttle board, right? They'll take the throttle board and cap it off totally. There's no need to do that. Your delta sensor will certainly show you a change. Before I forget, somebody mentioned here that the FLIR, right? An infrared gun, that's just a brand name of FLIR. There's certainly other ones out there. But when they said FLIR, he meant we could have measured the exhaust manifold runner. Now, obviously, a cylinder that's not firing is going to be colder, relatively speaking, than the ones that are firing. It doesn't necessarily prove there's a restriction. Keep in mind, if we can't make the cylinder exhale, we're not going to have combustion to begin with. So that runner is going to be cold regardless. I hope that makes sense. Now, if it was a restricted cat, you know what I mean? Or the runner was further downstream and we could have some kind of combustion in that cylinder, we might see a temperature drop across that restriction. But that same restriction is not allowing combustion to occur at all. Because if we can't get the exhaust gases out, we cannot get fresh air and fuel in, and it will not support combustion. So excellent idea, but you might not be able to rely on that conclusively. It will certainly tell you the cylinder's misfiring. It does not mean that it's an exhaust restriction. You got any more good ones for us, Brent? You're muted, bud.
Jason asked why cranking and not running. I believe he was referring to the crankcase case study.
Now, I know we did not get to this section. I have an entire section at the end of this class devoted to how and why, under what operating conditions to capture this data. My blanket statement is cranking, idle, snap throttle with a decel, and power brake conditions. That will give you almost every running scenario that the cylinder should experience. Some leaks only occur under cranking conditions due to clock time. Other faults, like binding valve guides and things like that, will not show themselves cranking, but will show themselves at idle. Some faults, like broken valve springs, will start, crank, and idle all day long and even run under relatively high throttle angles. However, when you snap the throttle and put a tremendous amount of energy into the spring and start the decel, then pop, 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 it'll start misfiring. So cranking, idle, snap throttle, power brake conditions. That's what you want to capture.
And that's specifically you're referring to in-cylinder captures, but most of the time, engine mechanical testing, you're doing the tailpipe cranking, same with intake pressure analysis, pretty much everything else you do cranking.
Yes.
Yeah.
And been very successful there. The only time I'll look at a running tailpipe waveform is when I'm trying to find a misfire. And that's steady state idle. That's not an elevated RPM. Oh, and if you are cranking an engine that is spitting and sputtering, you know what I'm talking about. When we disable a fuel pump and there's some residual pressure in the rail and you're cranking the engine and it's going, you know what I mean? That is no good. You want steady cranking cadence because we rely on that 720 event, that 720 degrees of crankshaft rotation. With the crankshaft to be relatively steady state at the entire time. When it changes speeds, we can't accurately partition the waveform. You know, from one piston's event to another might take this long, and from that same piston event to another piston might only take this long. It's got to be split up evenly.
He follows it up with a response that says, because of time, ? And I think you answered that. Basically, cranking speeds, you have more time for that volume, loss of volume.
Even a perfectly good engine is going to look crazily erratic by way of pressure transducers if the thing is spitting and sputtering due to variations in fueling when you're cranking. If that fuel pump's giving you heck and you're cranking, I mean, just be patient. Hold the throttle open, snap the throttle a few times. You know, try and clear the fuel out to the point that the engine will just crank over. Your pressure waveforms are useless if the crankshaft speed is going up and down. It's not going to work.
How much is the difference between cylinders to log a fault on relative compression?
That's an excellent question. I think if you have a mechanical fault that you can hear, it's definitely going to be visible quite easily on a relative compression test. I don't know if I can hang a number on it. I'm sure an engineer could probably figure that out with some math. But you know, if somebody says if I have a 5% cylinder loss in compression, am I going to see that? Probably not. But you know what I mean? I just want to determine if I have a gross leak with a relative compression test. It's not a be all end all, but it's certainly the test I'm going to perform first.
It's a pretty dang good test, and it's a part of the puzzle piece. Like, right, if you're diagnosing a single cylinder misfire and you see that single cylinder is slight lower than the rest, maybe you need to investigate further. But if not, that's kind of maybe the best way. Just consider what symptoms you're trying to diagnose as well.
Look at it this way. Let's pretend I told you you weren't allowed to do a relative compression test. Are you still going to be able to find the fault with the car? Sure. It may help you. It may not. It's certainly very easy to do. It only takes 10 seconds. So if it doesn't help you, oh well, move on, right? You'll find out another way. More than one way to skin a cat.
Why did you choose an absolute vacuum transducer instead of a Delta style on some of your intake captures?
I prefer an absolute sensor over a Delta sensor because it lacks those goofy characteristics, like that bounce back characteristic. You're not going to see that on an absolute sensor because it's not as sensitive to change as the Delta sensor is. So in my opinion, it's a bit more stable. And for the same reason you like to eliminate noise from a capture by way of filtering, it kind of eliminates anything that could help confuse my process. So I urge you to use an absolute sensor cranking. I don't want to use my Pico on it because it's so expensive. But my vacuum transducer from ATS, for instance, is a third of the cost. So it works well for me.
I got to admit, the fact that it's inverted to what I'm normally used to, it drives me crazy. And some of the guys in the chat were complaining about that as well. You can buy adapters probably to reverse polarity, I'm guessing, on that.
Press your invert button.
Yeah, or invert it, right, on the scope.
Right.
How can we do a compression test on a hybrid car with no starter motor?
You have to disable the car from starting. I know Daryl's my Toyota buddy. Daryl, chime in there. How do you disable the Prius? There's what do they call that? Maintenance mode or something? When you crank the engine and it won't start? I forget what they call it, but that's procedural. It depends on the car. It could be a series of push buttons. You know what I mean? Turn on the air conditioning and hold the brake pedal and cycle the turn signals a few times. It's all up to the software. So, great question. Thanks, Daryl. He calls it service maintenance mode. And it's just a means to tell the car that, hey, look, I want to work on this engine. Please disable the hybrid system because I need to make this engine work so I can test it.
Yeah. He's referring to the fact that you got motor generators turning the engine over at 1,000 RPMs as opposed to a conventional starter.
Yeah. And when you put it in service maintenance mode, it's meant for things like that. There's a compression test you can run on the engine. For instance, I'm just speaking about Prius because I'm most familiar with that car, but it's procedural. What you're going to want to do is you're going to have to follow directions in service information to perform a compression test. Instead of using the gauge, you're going to use your transducer.
The other thing too is something I don't know that we brought up is there's a lot of vehicles that are including this stuff in scan tools.
Yeah, absolutely.
Some of them have been for years. So keep that in mind. It may be even easier than putting a current clamp on the car.
Yeah. And Tim Carpenter mentioned, I think what he says, it doesn't keep it from starting now. I think what he's talking about is it'll allow me to crank the engine up in that Prius and the hybrid system will function. Well, at that point, then disable the fuel system as well. It all depends on the car you're working on. Not every car can be disabled the same way. But if you want to measure pressures in the engine, cranking, you're going to have to find a way to disable the engine.
Jurgen says, do you use voltage drop measurement between engine block and B negative for relative compression? It will show humps on top.
It will certainly. The voltage drop across a ground, right? You're showing the voltage drop, the voltage difference in potential from one side of that connection to the other. If you zoom in tight enough, or you're utilizing a feature on some scopes called AC coupling that filters out the DC, you get like I'll call it a virtual zoom of that capture. And it will certainly infer starter load, which is relative compression. So yes, you can do it that way.
Would the exhaust runner restriction load the starter a certain amount?
Not the fact that it's restricted, but keep in mind, a relative compression test refers starter load when the cylinder's on compression. That exhaust valve is closed anyway, right? So even if you didn't have a manifold on that exhaust system, on that cylinder head, the relative compression test would still look identical. I hope that makes sense. Always understand the limitations of the test you're performing.
I guess they're thinking like kind of like your case study. If that restriction was severe enough, the companion cylinder would show an increase in starter.
I get it. Well, you guys saw the relative compression trace. There wasn't much difference, right?
I think,
Nothing
yeah. I think in that case, it just wasn't so much of a restriction that it showed up with the starter current on that one.
Right. If I go back to, I'm not gonna share my screen again. I'll just go back to. Oh, you know something? I had no numbers on that screen.
Yeah, there's no sync or firing.
There's no numbers on that screen. So, you know, if we produced 150 PSI cranking, I had 40 or 50 PSI back pressure. I mean, maybe. I'm sure if we zoomed in tight enough, once we knew what cylinder it was, there was probably one starter hump that was a little bit higher than the rest. And John Nigro said the same thing. There still had volume in the runner. So even though that exhaust runner was restricted, at idle at 800 RPMs, I produced back pressure, but maybe cranking enough air could get by that I did not have significant starter load increase. John, great point. Thank you.
Can you do analysis on diesel engine? I mean, all 4 tests.
4. I'm not sure what you mean by the 4 test. Do you mean like idle, cranking, running, and snap throttle? Is that what you're referring to? Please raise your hand if the answer is yes to that. Whoever asked that question.
That was Soren.
Okay. You're going to have to create a restriction across the inlet like that, so we can create the restriction that's going to show us the valve events. If you have back pressure, you will see it. If you have a cylinder that fails to fill, you will see it.
Soren also asked, can you do oh, that's the one I just asked. Maybe I closed the wrong question. Do exhaust pulses occur at simultaneous time of engine events or delay for exhaust gas traveling length of the vehicle? I think you're doing, if you're, you know, I guess you could talk about cranking for engine mechanical testing or misfire analysis.
Yes. Now, we did not have time to get to the misfire case study that I wanted to demonstrate. But yes, there will be offset, and there's definitely not enough time to get into it now. I think I'll just confuse you. But when it comes to misfire, yes, there's a time delay. Keep in mind that the compression event, the ignition strike occurs here. The exhaust valve opens not quite at 180, but maybe 40 degrees beforehand. So let's call it 120 to 140 degrees after the ignition strike. On a 4-cylinder engine, one ignition strike occurs between top dead center compression and the exhaust valve opening. On a 6-cylinder engine, 2 ignition strikes occur in that same time frame. On an 8-cylinder engine, 3 ignition strikes occur in that same amount of time. So you will have to offset by 3 ignition events on an 8-cylinder, by 2 ignition events on a 6-cylinder, and offset by 1 ignition event on a 4-cylinder. So if I'm referencing cylinder number 1 ignition strike, and I create a misfire on cylinder number 1, I will not see that occur until 120 degrees later, give or take. And that will line up almost with the 1-cylinder ignition event before that. So if the firing order is 1, 3, 4, 2, even though I reference ignition strike number 1, I will tell myself it's number 2 and then count it out. That'll help me pinpoint where my misfire is. Again, it's a really poor way for me to answer that question. I didn't want to disregard it, but there was certainly not enough time. I don't know how else to handle that. I apologize. We simply just don't have enough time to cover
I think
it.
that's the best for misfire analysis. Just think about when the exhaust valve opened for that synced cylinder and work your way out using
Put it this way. If you put your piston chart up there, that dip in the waveform that indicates the misfire occurred usually happens somewhere in the middle towards the end of that exhaust stroke, somewhere maybe 3/4 of the way through that exhaust stroke, and well within the meat and potatoes of that stroke. So no matter what you're using, a 4-cylinder, a 6-cylinder, an 8-cylinder, if I'm going to use my phone here, if this represents that exhaust stroke, it usually happens somewhere well within the middle. I hope that makes sense.
One thing you might try if you're not sure is just go ahead and put your pressure sensor in the exhaust, sync it up to number 1 cylinder, and get it running. And then just disable number 1 and see where the pulse shows up on the exhaust. You know, you get in some of these engines, like you happen to get a V10 or, God forbid, a V12 in the shop. You have, you know, it's really hard to tell. So, but if you're unsure, just set up a test and see what comes up. So
I'll tell you what, that's a lot of fun too. I used to play that game with a friend of mine. I'd go like this, and he'd unplug a coil, and I'd have to look at the data and tell him what cylinder he disabled. It's a great way to learn. Great way to learn.
Billy mentioned that you lost him on the switching of the firing order, and that was the case study where you have the exhaust valve not opening. I think the Jeep Liberty.
Okay, I'll tell you what. Since I have this on my screen right now, I'm going to share it. Now, if we were to look at this right here, we know this is top dead center compression, and we know this is top dead center compression, which would make this my 360 mark, 0, 720, 360. Right here is where my intake stroke starts. So if I referenced an ignition strike that occurred right here, let's say I called this cylinder number 1. If the firing order was 153624, 153624, right, ignition strikes. Number 1 ignition strike occurs here, but number 1 intake stroke is 360 degrees later. So when I initially looked at that skewed pattern that showed the pressure pulse and the intake, I knew this was ignition strike number 1. I automatically assumed this was intake pole number 1, when in fact intake pole number 1 was way over here. So whoever asked that question, does that make sense what I just said? Why it's offset 360 degrees? But Bryn, was that I just want to make sure the guy got it. And if you think about what's the significance of the firing order, halfway through the firing order would be halfway between 0 and 720. That's 360. So if I got the first 3 cylinders and the second 3 cylinders, 360 is where my nose is, big nose. I just take the first 3 and switch it with the second 3. 153624 becomes 624153. I hope that makes sense.
What are you using for inches of water? I guess
that is a tailpipe sensor. It's an absolute transducer that works just like the intake manifold transducer or the in-cylinder pressure transducer. It's just that it's scaled so tightly. It measures in 25 inches of water as its max output. There's 25 inches of water in 1 inch of mercury. So it's 25 times more resolute than the vacuum transducer, but it functions the same exact way.
George just produced some helpful information. He says the Cenex Technology First Look TM 4-cycle engine timing chart. I don't know where that's available, George. If you want to, I guess we could probably Google it. But he says that takes the crank speed into consideration, which would be interesting to see. I haven't heard of that.
I don't find if you're talking about variations in crankshaft speed, if the engine's constantly changing speed, I just don't trust it. If you can trust that test result, great. I don't trust it. There's too much at stake. So I want a steady cranking engine. If my engine's not cranking steadily, I will find a way to make it crank steady.
Oh yeah, I agree with you wholeheartedly. I wonder if he means uh, the normal changes in crank speed. I don't know. I'm curious now, but
As in per cycle, I mean per cylinder.
yeah,
Yeah,
I don't know.
you know, if they're all the same, it typically doesn't become a factor.
Tried to get the shop to buy this equipment. I got the cold shoulder. I'm going to invest in myself. Any discount codes? Was going to buy from Auto Nerds support, but they no longer selling. I don't know. It depends on what equipment you're looking for. ATS Advance used to sell ATS stuff. I'm not sure if they do anymore. You can talk to your sales rep. Um, Sometimes it seems like those sales reps can find just about anything. So give those guys a call.
Yeah,
Would be my answer.
100% spot on there. They
About,
can find anything.
about sales codes, probably, I don't know of anything, but those guys would know. What about the Zoom functions on WPS? We talked about that a little bit, Brandon, the first night. I personally like using the range functions, but you can use the zoom function, which is it makes that transducer kind of react more like a pressure pulse sensor, and the waveform, now is above and below zero, so it basically is kind of like AC coupling that signal. And it can be helpful for really low pressure changes like crankcase, maybe tailpipe or something like that. But I try to stick with the range 1, 2, and 3 functions if I can. Just experiment on those zoom functions on some really, really low pressure stuff if you'd like to give it a shot. Cut relay, I don't know that one. Times between, go ahead. Oh, okay. Times between valve opening events. I think it was about that chart. Times between valve opening events. Chart I printed yesterday is from year 2003. It's missing 3-cylinder engines, very common these days. Okay, that's that Cenex technology chart that George is talking about there.
Okay.
Bart Young.
It sounds like it could be of good use. Certainly, at least to gain an understanding for sure.
When I think that Scott, the drivability guys, their software does some pretty interesting stuff. I think there's some places where you can kind of put where exhaust valve and stuff events show up, and some of their software that it takes that stuff into consideration as well. But when using an absolute vacuum sensor, don't you have to somehow bleed off the trapped vacuum?
Well, we're not using a Schrader valve for starters, so nothing will be trapped. And the moment you stop cranking the engine over, you're referencing the atmosphere by way of the throttle plate. It's going to equalize the atmospheric pressure. I hope I answer your question correctly.
Why is there sometimes a vertical variation up in the delta sensor's captures in the intake, almost like an absolute sensor when vacuum is decaying and coming back, if that makes sense?
I refer to that characteristic as the bounce back effect, and that's not an official word. I just kind of made that up, and it reminds me of the example I gave in a couple of classes beforehand. Was, you remember those old paddle balls when we were a kid, and you had the little rubber pink ball that was tethered to the wooden paddle with an elastic cord, and you can just, if you hit it lightly, you can keep it on the paddle. If you hit it far, it'll go way out, but then it swings way back right before you throw it across the room because you ticked off. That same paddle, that same characteristic, when the ball goes out and comes back, the harder you hit the ball, the further back it flies. If you hit it lightly, it only comes back a little bit. That seems to happen with the delta sensor. It almost rings out, if you will. You pull way down, it'll fly way back up again.
Robert, you asked if we could use a WPS 500 on the tailpipe. You absolutely can. That sensor is amazing. It will do it for sure. Like I said a moment ago, I prefer range 1, 2, and 3 and try to use those. But if you want to experiment and try the zoom functions on the tailpipe, that would be a good place to try it. Is the waveform the same on a WPS intake as a vacuum sensor intake waveform, but different to a delta sensor? Absolutely spot on. The vacuum sensor, in the case of the ATS products, the capture is inverted from what the WPS would be. I'm in the market for Picoscope, WPSE, etc. That was Bernie before. Bernie, ask your sales rep for advance. They can surprise you sometimes. If you fall short there, reach out to Brandon or I, and we will definitely point you in the right direction. We got some friends that are really good for the industry that sell some equipment as well. So I think that's it.
Awesome. Man, this is a ton of fun. Thanks, guys.
Yeah, we went over quite a bit, but that's okay. Everybody approved of that, and so that's fine. I had a request in the Q&A to talk about the recorded classes, so I'm going to share my screen here for just a second and bring that back up. So first off, we want to thank all of you for signing up for this class. I know we've enjoyed it, and I hope that you have too. And I'm sure that based on the Q&A and the feedback and the chat, there was a lot of learning going on in these four nights of training. So that always makes us feel good that we're doing something that can make a difference. If you'd like to see any of the other topics that were recorded, those are like 1-hour sessions. You can go to our website, which is ctionline.com. Those sessions will be up at the top. There's a training tab. You click on that, and from the drop-down box, select Virtual Classroom. When you do that, any of those 1-hour technical sessions that are currently scheduled, will be there at the top. If you scroll down, you can see all of the sessions that were recorded, and you can view those at your leisure, and they are at no charge. These official classes, now we are going to be setting up some more of these classes through into this month and into August and probably September and beyond. So we encourage you all to visit our website regularly to check for any new classes that have been scheduled. Now these classes, you can find them under the Classes Near Me section. You don't have to put in any of the information. Just go to the bottom of that section and hit the search button. When you do that, all of the virtual classes that are currently scheduled will be there. There is a registration link there in red, but it is not active. You must copy and paste that link into either a Firefox or Chrome browser in order to access the registration page. These sessions, your class that we just had, the 4 sessions, they have been recorded. We will need time to edit them, and then they will be posted there on the website under that training tab, Virtual Classroom, for you to go back and view them again. We'd also like to encourage everyone, if you're on Facebook, please look us up at CTI WTI members and join our Facebook group. There'll be a lot of good information, tech tips, discussions, all kinds of things that are going on that on our Facebook page, and we would love to have you participate if you can. So if we have no other chats or questions, I think it's time for us to go to bed. So we will sign off for the evening. Again, for Brandon and myself, thank you for being here. We've certainly enjoyed it, and we hope that you will join us again for another session. Have a good evening. Thank you.
Thank you.
Bye.
Bye, guys.
Take care.